Good morning. Good morning to everyone. We will start the second day of the workshop. And the first speaker today is Professor Matthias Físicas. I don't. It's okay. Okay, so this is the presentation, and please, Matthias.
I would like to thank the organizers for inviting me to this conference, for celebrating the 65th birthday of Professor Stephen Wiggins. I have always admired his renowned book, Introduction to Applied Nonlinear Dynamical Systems and Chaos, which was one of my favorites in my master and PhD studies. I first met Steve in 2017 when I began as a postdoc in CHAMS, Chemistry, Mathematics and Phase Space, an EPSRC-sponsored grant involving 4 universities under his supervision. During my time in Bristol, Steve helped me to change my research perspective and involved me in many projects. His guidance was instrumental to my research work. I want also to say that Steve is not only a brilliant scholar, researcher, and author, but for me, the most important that he's exceptional mentor, teacher, and friend. His passion for science and his innovative teaching methods, his dedication to his students and postdocs was inspiration for me, and I try to embody his spirit and apply his teaching methods to my own work with my students. I'm grateful for his support in advancing my career, and I continue to enjoy working with him to this day. Happy birthday, Steve. One of the projects in which I worked with Steve was phase-space geometry and dynamical matching in caldera-type Hamiltonian systems. Despite the fact that we published 13 papers, I will try to give an overview of all this work. In all these years, we had also many collaborators and friends, I would say, like Victor Garcia Garrido, Makrina Gaoglu, Anna Manso, Haris Kokos, Markon Hillebrand, and the student Yiping Geng. Also, I want to say that Yiping Geng, I was supervisor together with Makrina, because Professor Stephen Wiggins gave us the opportunity to supervise students in CHAMS, and not only to us, but to all postdocs of CHAMS, and this is a good example what means good mentorship. Caldera potential arises in many organic chemical reactions. I cite some of the papers that use this model in these organic chemical reactions. This potential has a similar topography with this of an erupted volcano. This is the reason that they named this potential as caldera. It is characterized by a shallow minimum at the center, where we have a stable equilibrium point. Around the shallow minimum, the shallow minimum is surrounded by potential walls. On these potential walls, we have the existence of 4 index 1 channels, 2 of them for high values of energy. We present this using these black points, and the other 2 for lower values of energy. These violet points represent these lower index 1 channels. The region of the index 1 channels are the only regions where the trajectories can enter into and exit from the central region of the caldera. The region of the stable equilibrium point, it's like a decision point between 4 different paths that lead to 4 different regions of index 1 sands and to the exit from the caldera. And as we said before, the entrance is achieved only through the 4 different regions of index 1 sands. As you can see, this potential is symmetric with respect to the y-axis. Here we give the analytical expressions of the potential and the Hamiltonian of the system. And now we'll give some basic definition that we'll use in the next slides. Transition state theory is a classical theory developed by Wigner, Eyring, Evans, and Polanyi that calculates the rate of the reaction as the flux of reactive trajectories through the dividing surface. But what is the dividing surface? The dividing surface is one less dimension surface than this of the energy surface. And this surface distinguishes 2 distinct regions in the energy surface and forms the boundary between them. Also, it has the locally no recrossing property, which is equivalent to the Hamiltonian vector field being everywhere transverse to the dividing surfaces, and this means that there is no point tangent to the dividing surface. The dividing surface is constructed in Hamiltonian systems with 2 degrees of freedom, using periodic orbits that are one-dimensional objects in the phase space. And, but for Hamiltonian systems with 3 or more degrees of freedom, for many years we used normally hyperbolic invariant manifolds. But this has many problems in calculating the normally hyperbolic invariant manifolds and complexity challenges. And the last years we developed with Professor Stephen Wiggins a generalization of periodic orbit dividing surfaces in Hamiltonian systems with 3 and more degrees of freedom. In this slide, we'll explain a little the framework of this problem. We depicted in the configuration space here the curve zero velocity that is depicted by these Biot curves. These black lines are the projection of periodic orbit dividing surface in the configuration space that coincide with the projection of periodic orbits in the configuration space. We consider that we have molecules of chemical substances. For example, we symbolize as A, B, C, and D that are at the regions of the index 1 sands. We consider that the molecules of C and D are stationary at the regions of lower index 1 sands, like to expect the molecules to be reacted. And the trajectories that have initial conditions on the dividing surfaces of upper index 1 sands represent the motion of molecules. And we consider that we have a reaction when these molecules cross the dividing surface of lower index 1 sands. For example, for the trajectories of A, corresponds to molecules of A, when they cross the dividing surfaces of lower left index 1 sands, they react with the molecules of C, and we have a bimolecular reaction and one kind of products. But when they cross the dividing surfaces of lower right index 1 sand, they react with the molecules of D, and we have another kind of products. According to statistical models, in the papers that we cited in the previous slide, the ratio of products should be expressed, the symmetry of the potential should be expressed to the ratio of products. But in many simulations and experiments, we know that this is not true. In many cases, we have the phenomenon of dynamical matching. This means that all trajectories that have initial conditions on the dividing surfaces of upper index 1 sands go straight across the caldera and exit through the region of the opposite lower index 1 sand. This means that 100% of products come out from the one region of lower index 1 sand. The desire to understand this fact was the motivation to study the phase space geometry of caldera. Initially, we studied the phase space in the neighborhood of unstable periodic orbits of upper index 1 ensemble. Here we represent the Poincaré sections in the neighborhood of these unstable periodic orbits for a value of energy above the upper index 1 ensembles. We present, using these black points, the unstable periodic orbits of upper index 1 ensemble. And these cyan and orange curves represent the unstable and stable invariant manifolds of these unstable periodic orbits. At the center, we see, here we have at the center, we have the point of the family, the point of the periodic orbit of the central family. We can see in this figure that even that the family of central minimum starts initially stable, for this value of energy is unstable, has become unstable. This is the reason that also we computed the invariant manifolds of this periodic orbit. As we can see, here we have a gap between the invariant manifolds of unstable periodic orbits of upper index 1 ensemble with the central region of the caldera. This means that the stable manifolds bring trajectories far away from the central area of the caldera to the neighborhood of unstable periodic orbits, and then guide the trajectories far away from the central area of the caldera to the infinity. This can explain partly the dynamical matching, but in order to understand better this phenomenon, we stretch the caldera potential in the x direction using stretching parameter lambda. This parameter equal to 1 corresponds to the classical case of the caldera. Decreasing this stretching parameter, we have the corresponding stretching cases of the caldera. Initially, for decreasing values of this stretching parameter, we observe again this phenomenon of dynamical matching, but there is a critical value where we start to have trapping in the central area for a small interval of time, and decreasing more the stretching parameter, we start to have more trapping, and also many trajectories start to exit through also from the other region of the lower index ensembles. To understand this, we depicted here again a Poincaré section close to the neighborhood of unstable periodic orbits of upper index 1 ensembles for a stretching case of caldera that corresponds also to trapping of trajectories in the central area of the caldera. Here we see that here we see again that the invariant manifolds of this unstable periodic orbit start to interact with the central region of the caldera. This means that they can guide trajectories to the central region of the caldera. And here we have invariant curves around the stable periodic orbits of the central family. Here we must say that for the stretching case of the caldera, for this value of energy, the periodic orbit of central family remains stable. In order to understand better this phenomenon, we use Lagrangian descriptors to compute the invariant manifolds. Lagrangian descriptors helped us a lot because we can compute the invariant manifolds in a region. For example, in this case, in the first column of figures, we depict the unstable invariant manifold from the upper left index 1 ensemble. The pink curve represents the curve zero velocity on Poincaré section. And the blue lines are the stable invariant manifolds that exist in the central region. In the second column of figures, we represent the trajectory that corresponds to the yellow point in the first column of figures. And the black line corresponds to the forward integration, and the green line to the backward integration. Lagrangian descriptors help us a lot because we can compute all the stable invariant manifolds that exist in the central region. Otherwise, with a classical method, we had to compute all unstable periodic orbits and to compute again the stable invariant manifolds. We see that in a case before the critical value of stretching parameter, we see a gap between the stable invariant manifolds and the unstable invariant manifolds of the unstable periodic orbits of upper index Swansons. But for the critical value, we start to see the formation of lobes between the stable invariant manifolds that exist in the central region and the unstable invariant manifolds of the unstable periodic orbits of upper index Swansons. If we take an initial conditions inside this lobe, we see that this trajectory starts to be trapped in the central area of the caldera before it exits from this through the region of the lower index Swanson. This means that these lobes between the heteroclinic intersection of the invariant manifolds is responsible for the trapping of the caldera. If we decrease more the stretching parameter, we have the formation of bigger lobes, and the trajectories stay for a larger interval of time in the central area of the caldera before it exits through the regions of lower index Swansons. This can explain the non-existence of dynamical matching, but in order to understand why the invariant manifolds have this behavior, we depicted for one value of energy above the upper index Swansons the non-stability index parameter of these unstable periodic orbits versus the stretching parameter lambda. I remind that for lambda equal to 1, we have the classical case of the caldera, and decreasing this parameter, we have the corresponding stretching cases of the caldera potential. Here, the figures, we have two regions. The one region corresponds to dynamical matching, and we depict this region using this blue arrow, and the region that corresponds to to the non-existence of dynamical matching, and we use this red arrow. We see that also a yellow line that corresponds to the critical value of stretching parameter. Initially, we see that the non-stability index has some fluctuations, a small plateau with small fluctuations, and after the value of 0.8, we have an ongoing reduction, and this means that the periodic and the unstable periodic orbits lose the ability to repel the orbits in the neighborhood, and to guide the trajectories far away from the central region of the caldera. This ongoing reduction of non-stability index happens until the non-stability index has been diminished sufficiently, and then the invariant manifolds start to focus and start to interact with the central region of the caldera. After this critical value of parameter, the stability index continues to decrease, and this can explain, we have the formation of bigger lobes between intersections of the unstable invariant manifolds of unstable periodic orbits of upper index Swansons with the stable invariant manifolds that exist in the central region of the caldera. Now, we want to explain the mechanism of the trapping of trajectories and the exit from the caldera. We can distinguish these cases according to the characteristic diagram. Characteristic diagram, I will give this definition from dynamical astronomy. This is my initial field of research, especially particularly galactic dynamics. We plot the x-coordinate of periodic orbits on the Poincaré section versus a parameter of the system. Here is the energy. Here you can see the red regions correspond to the stable periodic orbits, and the cyan regions correspond to unstable periodic orbits. Initially, we have the family of the central minimum that is stable. Here is the first case. The second case, we have a period doubling bifurcation. Here you can see the two arches of this family that is initially stable. In this case, we have a transition for the central family from stability to instability. The third this is the second case. The third case it is relevant with this transition of the period doubling family from stability to instability. In this case, all families are unstable. And the fourth case, the last case, it is because a second period doubling bifurcation that is initially unstable. And in this case, the family of the central minimum becomes again stable, and we have that two period doubling families to be unstable. In order to understand better this mechanism, we plot the Poincaré sections in the central region of the caldera. Here we see invariant terms around the central stable periodic orbit of the central family. This means that there are many trajectories that remain forever in the central region. And but outside the regular region, we see 10 green regions that correspond to invariant terms around a stable periodic orbit with period 10. And we depict the associated unstable periodic orbit with period 10 using these 10 black points. We computed again here the unstable and stable invariant manifolds of these unstable periodic orbits with period 10, and we see that many trajectories are trapped in the lobes in these between homoclinic intersections, and eventually are guided from the invariant manifolds, unstable invariant manifolds, to all available phase space, and of course to the exit from the caldera. In the second case, that as we said, we have it is after the first period doubling bifurcation. The transport is possible because of the unstable periodic orbit of the central family. Because here, the periodic orbits of the central family becomes unstable and are guided through the and are guided by the invariant manifolds of these unstable periodic orbits to the exit from the caldera. We can see also invariant curves around the 2 points of the new period doubling family. In the third case, all periodic orbits of these two families are unstable and play the role of the unstable periodic orbits that we saw in the previous cases. In this case also we have many heteroclinic intersections and the lobes between these heteroclinic intersections, and also the manifolds of both of periodic orbits can guide the trajectories to the exit from the caldera. In fourth case, we have also many trajectories that remain in the central area of the caldera, around the stable that lie on the invariant ori around the stable periodic orbits of the central family. And now, the unstable periodic orbit of the second period doubling bifurcation plays the role of the previous unstable periodic orbits, and we have trapping of trajectories between these homoclinic lobes, and they guide, and the unstable invariant manifolds of these unstable periodic orbits guide the trajectories to the exit from the caldera, and in all available phase space. Now, except bifurcation of periodic orbits, we have also bifurcation of critical points. If we vary the parameters C1 and or C2, we have a pitchfork bifurcation of equilibrium points. here in this diagram, characteristic diagram, we see initially the family of central index 1 saddle, and here we have a pitchfork bifurcation. The red and the green correspond to the families of lower index 1 saddles, and at this point, the initial family of index 1 saddle becomes stable. This means that the classical case of the caldera is a product of a pitchfork bifurcation, because before the bifurcation, we have a caldera potential that has 3 index 1 saddles, 2 upper index 1 saddles, and 1 central index 1 saddle that control the 2 lower exit regions. And after this bifurcation, we have the classical case of the caldera, because we have 2 new families of lower index 1 saddles that control the 2 lower exit regions, and a stable equilibrium point at the center. From this work, we understand that actually the classical case of the caldera is a product of this pitchfork bifurcation. What happens in the case of the caldera with 3 index 1 saddles? We have 3 types of trajectory behavior. We have trajectories that start for the initial conditions for the trajectories that have initial conditions on the dividing surface of unstable periodic orbits of upper index 1 saddles. We have 3 types of trajectory behavior. The one type is the 2 types are trajectories that exit through the 2 different lower exit regions, and trajectories that remain for long time intervals in the central region of the caldera. In the second figure, we depicted the ratio of trajectories that belongs to the reactant part. This means that the exit through the opposite lower exit region, and the black line represents the ratio of trajectories that exit through the other lower exit regions, and also includes the trajectories that remain in the central region of the caldera. We depict this ratio versus the parameter C1 of caldera potential for a value of energy above the upper index 1 saddles. We see that the ratio of trajectories that have initial conditions on the dividing surface of unstable periodic orbits of upper index 1 saddle and exit through the opposite lower exit region initially increases, and after some fluctuation it has a small plateau, and at the end of this plateau it converges to 1. This means that 100% of trajectories live from the opposite lower exit region. This corresponds to the dynamical matching, because we have the 100% of trajectories to go straight across the caldera and exit through the opposite lower exit region. The opposite behavior we have for the black line, and at this point, that's at the end of this plateau, corresponds to the transition from the caldera with 3 index 1 saddles to the caldera with 5 equilibrium points, 4 index 1 saddles and 1 stable equilibrium point. This means that the non-existence of dynamical matching also is related also with these pitchfork bifurcations. For caldera with 3 index 1 saddles, we have no existence of dynamical matching, but for the classical case of caldera, we have the phenomenon of dynamical matching. The transport, in this case, is similar with the classical case of the caldera for the trapping of trajectories, but with the only difference that the exit from the caldera now is controlled only from 1 index 1 saddles at the center. In this case, we depicted the unstable invariant manifolds of the central unstable periodic orbits of the central index 1 saddle. And we see that here we have 2 directions of the unstable invariant manifolds at the center. If we take 2 initial conditions, one on the left and one on the right, we see that the corresponding trajectories exit through the left exit regions and through the lower right exit region. This means that these unstable periodic orbits share the K in the central area of the caldera and control the exit from this through the unstable variant manifolds. Now we break the symmetry with respect to the y-axis, and we start the asymmetric caldera. In this case, we have the coexistence of these two phenomena, and we have on the one side the phenomenon of dynamical matching for the upper right index transant, and for the upper left index transant, we have trapping in the central region of the caldera and also exit through both of lower index transants. This happens because here we have the coexistence of these two phase space mechanisms. Here we have the phenomenon of dynamical matching and the gap between the invariant manifolds with the central region of the caldera, but here we have interactions of the stable variant manifolds of the stable periodic orbit of upper index transants with the stable variant manifolds that exist in the central region. Here we have a new type of dynamical matching because the coexistence of this phase space mechanism. Now we'll give an overview of three-dimensional caldera. Actually, we added an harmonic oscillator in the z direction. As we can see here in three-dimensional contours, the potential walls extend also in the z direction, and also for different slides in the z direction, we have a similar topography with this that we have for z equals 0. This means that it's a natural extension of the two-dimensional caldera, but here we have the problem that we cannot easily to compute dividing surfaces. For this reason, we used a new method, generalizing the periodic orbit dividing surfaces. In many years, they believe that we can construct periodic orbit dividing surface only in Hamiltonian systems with 2 degrees of freedom, with a classical algorithm of Petsukas and Pollack, etc. In Bristol, we had the idea with Professor Stephen Wiggins to generalize this notion in order to avoid difficult calculation of normally hyperbolic invariant manifolds. And we constructed 2 algorithms. The first algorithm has one necessary condition. I want to say, to highlight that I will not get in details, mathematical details for the construction of this dividing surface and the geometry of these surfaces, because it's another, we have published 12 papers to this. And I will briefly give you an idea of the construction of this periodic orbit dividing surface. The condition that we need is the projection of the periodic orbit to be a closed curve in a 2-dimensional subspace of the configuration space. If this is true, we have the second version of the first algorithm. In the second version of the first algorithm, we construct a torus from the Cartesian product of the projection of the periodic orbits with n-2 cycles in the configuration space. We try, in Hamiltonian system with n degrees of freedom, we have n-dimensional configuration space. We take the projection of periodic orbit in this configuration space. We have 2 coordinates, and we have other n-2 coordinates. These coordinates, we construct a circle in every subspace of the configuration space, and construct these n-2 circles, the Cartesian product of the projection of periodic orbits with n-2 circles, until we fill all the coordinates for different circles. Then we create, we take this from the classical algorithm of Pollack and Petsukas, and we add n-1 additional segments, adding the dimensionality of the initial object, of the initial geometric object. Then obtain the last momentum from the Hamiltonian. Now, what happens if the first condition is not true? We have a second condition. In this condition, the periodic orbit is a closed curve in a 2-dimensional space of the extended configuration space. We define as extended configuration space the configuration space plus 1 momentum. In this case, we have the first version, and we construct a torus now from the Cartesian product of the projection of periodic objects with n minus 1 cycles, because now we have in the initial project one coordinate from the configuration space and one momentum. Then we have the creation of n minus 2 additional segments using n minus 2 momenta, and obtain the last momentum from the Hamiltonian. These algorithms give us the dimensionality and rotatability of these objects, but they cannot give us the local no recrossing property. For this reason, we studied these surfaces in Hamiltonian systems that we have analytical expressions of periodic orbits, of dividing surface, of everything, and we proved the local no recrossing property for two cases, for the quadratic normal form Hamiltonian system and the quartic normal form Hamiltonian system. Also, the last project was with the help of Francisco González Montoya. And also, we extended this notion in rotating cases of Hamiltonian systems. Now, what happens if both of the conditions that we had before are not true? We use the second algorithm. That I don't prefer this algorithm because in the first algorithm I control the geometry of the surfaces, that is actually are toroidal structures. And here we don't know initially if this will be toroidal structure or cylindrical structure. This is the reason that I prefer the first algorithm, but this is a last option in order if the two previous conditions are not true. Initially locate the periodic orbit. We construct of an object from the Cartesian product of the projection of the periodic orbit with n minus 2 cycles in the configuration space. Here, actually, you see that is something similar to the previous algorithm, but what happens here? Because in the previous case, we know that the projection of periodic orbit is a closed curve. We can understand that we will have a toroidal structure taking the Cartesian product. But here, if it's a line, the configuration, this subspace of the configuration space, we may have cylindrical surfaces from this construction. Then we create n minus 1 additional segments using the n minus 1 momenta, and we obtain the last momentum from the Hamiltonian. Again, for this algorithm, we proved the locally no recrossing property in Hamiltonian systems that we have analytical expression for this. And we prove it, and this is, we have published about these 12 papers. In the break, if you are interested, we can discuss the geometry and the details of this construction, because it's not the subject of this talk. Now we use these new periodic orbit dividing surfaces. We construct the new periodic orbit dividing surfaces in the three-dimensional caldera. The trajectories now that have initial conditions of the upper index one suns in the type 1 for the type 1 trajectories, forward and backward. Here the red lines and the black lines correspond to the forward and backward time integration, and the green surface represents the curve 0 surface. We see that both of them have directions to the opposite region of the lower index one channel. For type 2 trajectories, we have that forward and backward, the trajectories go to the infinity directly. For type 3 trajectories, forward, we have that the trajectories exit through the opposite through the region of the opposite lower index one channel, and backward go to the infinity. And for the type 4 trajectories, we have the opposite behavior. And now we have to explain for the type 1 and type 2 why we have this behavior forward and backward to have the same direction. We make the hypothesis that this is because of these trajectories belong to the lobes of homoclinic intersections of the NIMS. In the one case of the NIMS corresponding to the upper index one suns, and the other case to the homoclinic intersections, the lobes between homoclinic intersections of the limb of the lower index suns. In order to check this hypothesis, because we have that forward and backward go to the same direction, we used Lagrangian descriptors, but now, because we have on point sections, because we have a four-dimensional point sections, we take, for example, one initial conditions from the set, for example, of type 1 trajectories. We fixed three variables according to the values of these initial conditions. And then we computed the invariant manifolds using Lagrangian descriptors. And we found that these initial conditions are always in lobes between these homoclinic intersections. This gives us an idea that maybe this periodic orbit divided surface can detect the homoclinic intersections of the invariant manifolds of the NIMS. And also, now we are working in a project that we can detect heteroclinic intersections of the NIMS, of the invariant manifolds of the NIMS. Another subject is what happens with the construction of this periodic orbit divided surface. Because this periodic orbit for one periodic orbit, we have many periodic orbit divided surfaces. According to our studies in integral case of Hamiltonian systems, we know that this radius has a limitation, has a maximum for this computation. But in non-integral cases, we cannot find this maximum. This diagram helps us to find this maximum value in order to depict the ratio of reactant parts and non-reactant parts for different radius of construction of these periodic orbit dividing surfaces. And we found that convergence after 0.2, and this, from this zero, we can trust and we can construct the periodic orbit dividing surfaces. But this is easy in 3 degrees of freedom. What happens in more degrees of freedom? For example, we want to study a caldera with 10 degrees of freedom, with 20 degrees of freedom. In this case, also it's a project, it's an ongoing project, because we have now a funding from Academy of Athens for AI and machine learning Hamiltonian dynamics. And me and Professor Stephen Wiggins will supervise a postdoc and PhD student in the next year in order to use method of vector support machines and particle swarm optimizations in order to understand and to find and to detect the optimized radius for the construction of this periodic orbit dividing surface. Here we summarize the conclusions for all this talk. I think time, okay, I finished because the time is, okay. Again, happy birthday, Steve.
Thank you. There are some questions or remarks?
So it's the first part of the talk where you had the scaling parameter. So that's just scaling the momenta, right? Or in the momentum part?
What means the construction of periodic orbit dividing surface?
The lambda.
Lambda.
The parameter lambda, which is the scaling parameter.
The first part.
First part.
Yeah.
So it multiplies the momentum, is it? Like you scale the momentum?
No, in the x direction. It's we put in the potential stretch parameter.
The potential is scale. Okay.
Yeah, in the potential. Yeah.
Okay. Because I guess if you choose
in order to stretch the potential, the upper induction suns, not put this in the potential.
Yeah, I'm just trying to. Okay, so I'm trying to make physical contact with what that means in the context of a reaction, right? So usually that lambda, so it's not a scaling potential, right? So in other words, things don't scale. It's a non-scaling potential in general, right? What you take.
Yes. Yeah. No. You mean that the non-scale that here is.
It's not a homogeneous potential, right?
Yeah.
It's not a homogeneous.
Yeah, you can check with also
okay.
the momentum.
So the different lambda will correspond to actually different possibilities. Like if I think in terms of molecules, different possibilities. So you're saying for certain molecules and similar energies, you will not have dynamic matching, and certain other, you will have dynamical action.
To check this. Actually, this is the idea of the initial paper of Collins et al. With Carpenter and Stephen Wiggins and all of this, to understand the existence of dynamic action, because in this, for this time, very many years ago, we didn't know that actually the classical caldera is a product of the pitchfork bifurcation. We found it later. This.
Okay.
This is the reason.
Okay, thank you. No more questions? Oh, sorry.
So when you added the asymmetry and you could essentially skew the reaction channels so it didn't go out one, can you turn that on and off? Essentially, can you make it like a spigot so you can have one reaction channel or the other? But
yes. We can do this. Yeah, we can do this. It's one of the future plans, and also to add time-dependent forces, and also to study the dissipative cases of caldera, and also the rotating case of the caldera. Because now it's no rotating systems. Yeah. There are many things that we have in the future. It's only the beginning, actually.
Okay. Thank you very much. So we thank again to the speaker. Thank you very much. And we will move to the next speaker. So, next speaker is Harris Skokos, and is the title of his lecture. So, please.
I suppose you can hear. Yeah, you can hear me. Good morning, everyone. It is really a pleasure to be here in Madrid, and well, I will start by saying what most of the people have said already. I really thank the organizers for inviting me and giving me the opportunity to be here and celebrate with Steve, but also for helping my students, because actually my whole group from Cape Town is here. We're not that big, but still, that was an exercise for all of us to be here. So thanks again to the organizers, and it is really a pleasure to be here and celebrate with Steve. I mean, we have heard so many things about Steve. Okay, he is a force of nature. He has, yeah, that's true. Actually, he has done influential work in so many areas, and we have heard yesterday many things, and he has influenced many people. And as we said, heard also in the previous talk. And I was really very privileged and happy to collaborate with Steve in the last couple of years, and we have published a few papers, and that's what I am gonna. One of the works that we did together is the thing that I will present today. And as you see, my title is Using Lagrangian Descriptors that we have heard so many times here in order to quantify chaos. This is one of the main research areas that I have been working over the years, how to develop numerical techniques which can detect chaos reliably and faster than the maximum Lyapunov exponent. And I have done, I and my collaborators have done some work in this direction, but then a few years ago when I started having some interaction with Steve, I thought that it would be nice to try to see how we can use Lagrangian descriptors for this purpose, and I think that we have some good suggestions about that. So as I said, this is a work done with many people. Sebastian Zimber, who is now doing his PhD in Germany, he was a master student in my group, and actually these works are his master thesis. And Malcolm Hillebrand, who is in the audience, Arnold Nagabasare, who was a postdoc in my group, Mattheos, the previous speaker, and of course, Steve. So, as you can see here, I come from Cape Town. This is our university, just to give you a glimpse of our university. It's really nice. We are not in the woods, in the forest. Here is the city, but you do not see it. It's not that far away. That's another glimpse of our university, and yeah, this is promotion of our city. Come and visit. Now, when I was invited to come here and celebrate Steve, I thought, where have we crossed paths? And that was many, many, many years ago. And this was done in 1995 in a here in Spain, actually, in Sagaro, which is in Costa Brava, north of Barcelona. There was a conference, a very good conference, actually, organized by Carl Simon. And we were there, and this is the proof, this is the proceedings. Here is his contribution, and later on my small paper. So we were there, Steve, although at that time we didn't have any interaction. And it is nice. When I was preparing that, I got scared because I realized that this is 30 years ago. That's a lot of time. And then when I came here, this became more scary because I realized that many people in the room, don't raise your hands, were not even born at the time. Yeah, so that's scary, but it looks like yesterday. Then the other thing is I tried to see if I had any photos from that era. And just for the younger generation, there was a time, not that far back, I hope at least, that you were taking a photo, you could not see it, you had to go back home, take all the 24 or 36 photographs of your film, go to the photographer, give the film, wait a couple of days for them to develop, and then you will see that the photos were out of focus. So, unfortunately, I didn't find a photo of Steve, sorry. I have a photo of, that's me, young and restless, and some Greek gang here, Tassos Boundis, Vasilis Rothos, who was a PhD supervisor of Macrina, and some other people like Zach Lascar, Silvio Ferrazmello here. So that was from that conference. Steve was probably behind, was not in the photo. So yes, that's interesting. 30 years ago or something like that, we are crossing paths, Steve. So it was really a pleasure working with you, and happy birthday again. Okay, now what I'm gonna discuss today. As I said, I will describe a little bit the Lagrangian descriptors and a chaos indicator that we have developed some years ago, which is called smaller alignment index. And then I will use the Lagrangian descriptors in order to devise some numerical techniques to quantify chaos. And there are 3 different indicators that I will use. And I will apply all these things in some simple prototypical models in order to convince you that there is some value with these numerical techniques, the Hannon-Heil system, the 2D standard map, and the 4D standard map. So my field is Hamiltonian dynamics, conservative Hamiltonian dynamics, so no dissipation. So that's the area where I will apply all these things. Okay, so this sounds like an insult to explain to you what is the Lagrangian descriptors, but why not? There are so many young people here, it might be a good idea to refresh their memory. So if we have a vector field dynamical system described by that, the initial definition of the Lagrangian descriptor was just the length of the trajectory in the phase space. And here I mentioned some basic papers on that. So we can integrate forward in time. So then we have the forward time Lagrangian descriptor. We can go backward in time, and we will see in a minute why this has some value. And of course, we can combine both things in order to have the general Lagrangian descriptor. And this tau is the time that we go forward or backward. And as we heard also yesterday, this has an impact on the pictures that we can get and the information that we can get for the dynamical system. So just to explain why we're interested in backward and forward in the integration in time, again, most people already, if not everybody, has a good understanding of that. If we have the forward time Lagrangian descriptor for this very simple Hamiltonian, and you color initial conditions on the phase space according to the value of the Lagrangian descriptor, you get a nice picture of the stable manifold. Doing that in the backward, you have the unstable manifold, and if you combine these 2 things, you have both manifolds, which is a very good representation of the dynamics of the system. Now, we also heard that yesterday. An advantage we have from these color plots, and here I have a simple example of the Duffin oscillator, the phase space of the Duffin oscillator, values, initial conditions are colored according to the value of the Lagrangian descriptor, the general Lagrangian descriptor backward and forward. And here you see the homoclinic orbit and the saddle point, the centers. And if you take the values of the Lagrangian descriptor along this line, you get this picture. And you can see the correspondence of these cusps where we have crossing of the manifolds. So using these cusps, you can identify the manifolds. And Mattheos, in the previous slide, also mentioned that he was extracting the manifolds, and that's how he was doing that. And we will come back to this kind of idea of seeing the values of the Lagrangian descriptor along a direction in the phase space. And here I have a simple example taken from this book, where Steve, of course, was also involved, where you have the Henon-Heil system and the phase space, and you can see the structure of stable and unstable manifolds, and by just finding the cusps, you can extract the manifolds, which gives you a very good understanding of the phase space. Here I'm using a slightly different definition of the Lagrangian descriptor. The difference is here we have an exponent p, and I use the value 1/2 because, according to many people more experts than me on the index, this has the advantages of revealing things easier and faster and more clearly. And from this point on, when I will say Lagrangian descriptor, I will refer to this p definition. But in reality, it is just that more or less the length of the trajectory in the phase space. Okay, so that's the small recap about Lagrangian descriptors. Now, when we want to quantify chaos, what can we do? And again, I remind you, I'm working with conservative systems because in conservative Hamiltonian systems, we have either regular orbits or chaotic orbits. And the nature of the orbit cannot change because we do not have time dependency. So an orbit is either regular or chaotic. It could be weakly chaotic, which means that the chaoticity requires a lot of time to be revealed, but it is either that or the other. And one thing that people have been using for many, many years is the computation of, or the estimation actually, of the maximum Lyapunov exponent. What is the maximum Lyapunov exponent? Again, I'm pretty sure that practically everybody is aware of that, but since we heard yesterday, not different definitions, but different approaches of practically measuring more or less the same thing. So we have an orbit in the phase space, and we want to understand if this is chaotic or not. We have a small perturbation, a small variation of this orbit, what I call initial deviation vector, this v. We let that evolve, and we compute this quantity, the stretching, the logarithm of the lengths divided by the time, and when this limit is computed for t going to infinity, this is the maximum Lyapunov exponent. Of course, numerically, you cannot compute a limit to going to infinity. What you do is you compute this quantity, the finite, this lambda capital, the finite Lyapunov exponent, and if we have regular motion, the maximum Lyapunov exponent should be 0, and the lambda capital, the estimator of the maximum Lyapunov exponent, goes to 0 following practically a power law of t to the minus 1. And here you see one of the first computations of Lyapunov exponent in 1976 from a paper of Benettin et al., where we have this kind of behavior in log-log scale, and you see the slope minus 1. When we have chaotic motion, they were calling that stochastic at that time, this quantity is positive. So this is the maximum Lyapunov exponent, and we have heard, and everybody knows that actually people doing completely different things from, I don't know, physics, they know about Lyapunov exponents, and that's the standard tool. What we did quite a few years ago, I don't want to talk about years, but some years ago, we defined what we call the smaller alignment index. The idea is the following. When you want to compute the maximum Lyapunov exponent, you start with a small deviation, as I said here. Now, there are two numerical approaches. One is you have your initial orbit, and you go and you have a nearby orbit that you can integrate with the same equations of motion, and the distance between these two orbits is this deviation vector. There are some technicalities there. This distance can become very large. You have to renormalize, do things like that. The other approach is to write down the equations that govern the evolution of small perturbations. So in some sense, some kind of Taylor expansion. This is called the tangent map for mappings, or the variational equations for Hamiltonian systems. So we know that when we want to compute the maximum Lyapunov exponent, we do not pay much attention on what is your initial deviation vector, because you know that unless you are very unlucky and you have to wait a lot of time, in general, you will find the same maximum Lyapunov exponent. So any two different deviation vectors will eventually give you the same result. And the idea behind the SALI is exactly that. We follow two different deviation vectors, and we have the initial condition of the orbit. We have the deviation vector. We evolve it either, as I said, with the variational equations for Hamiltonian systems or the tangent map for mappings. And we follow two different initial deviation vectors. And we just normalize them from time to time to have norm 1. And we compute the norm of the sum and the norm of the difference of these two vectors. And we take the minimum. That's why we call it smaller. And the reason why we call it alignment, because it is quite simple. When this quantity goes to 0, the two vectors are having the same direction or completely the opposite direction. And when that happens, this happens when we have chaotic orbits. Because when we have chaotic orbits, no matter what is your initial deviation vector, eventually you will have the same evolution. The two vectors, or even more if you want, they will align to the same direction. And let's see an example, an application of this tool to our beloved Henon-Heil systems. Here we have the Poincaré section, and we have three different orbits. This black orbit creates these 5 islands. This is obviously a regular orbit, and if you plot the SALI, the logarithm here, this is logarithmic scale, you see the black curve remains practically constant. Okay, some fluctuations. If you take the red orbit, this is a highly chaotic orbit in the big chaotic sea. You compute SALI after some transient time. This is 10 to the 2, 100 time units. You have an abrupt drop of this value to 10 to the minus 16. That's 0. And this blue curve is what I call somehow sticky orbit. It starts at the borders of a bigger island. It stays there. You see it creates this kind of zone, and then eventually the blue points go into the chaotic sea. And again, we have the same behavior. The SALI more or less stay constant or has very large values in log scale, and eventually at some point it goes down very fast, which is a sign of chaoticity. And actually this drop happens before these points leave this zone of surrounding the island of stability. So, and we also have some theoretical predictions which have been numerically confirmed that this exponential decrease happens according to e to the minus lambda 1 minus lambda 2. Lambda 1, the maximum Lyapunov exponent, lambda 2, the second Lyapunov exponent. But that's not that important. And if we use the different values that we can see here, and we color initial conditions according to the logarithm of the SALI, you can get these nice pictures where you can see quite clearly large values of SALI, regular motion. You see some tiny islands of stability. Black points correspond to very, very small values, actually practically 0. And of course, in between there are some points, some values there. So this is a good indicator. It is faster than the Lyapunov exponent, and we have applied it to many different systems. And just to show you another example, if we do it in a 2D map, here things are a little bit different, but not that much. So here we have a very simple mapping. This is the phase portrait. We have two initial conditions. This A is just a regular torus. It's a regular orbit. If you compute the Lyapunov exponent, you see that it goes to 0 with a slope -1 in log-log scale. Fine. The red orbit here corresponds to this small chaotic region, and you see that the Lyapunov exponent shows this kind of positive value. That means this orbit is chaotic, this is regular. You can see it also from the phase space. If we compute the Sally now, what happens is for the chaotic orbit, the red value, we have this very fast exponential decrease at 10 to the 2 point something. Let's say up here, you could see that this value is 10 to the minus 16. This is a practical 0. Now, what happens with the regular orbit? In the previous case, for the regular orbit, the two values, the Sally was practically constant. Why? We said that if we have chaotic orbit, the two vectors are aligned, Sally goes to 0 exponentially fast. What happens if we have regular motion? If we have regular motion, the two vectors do not align. They fall on the tangent space of the torus. And here, in this system, the torus is a two-dimensional object. There is no need for these vectors to have the same direction. But in this case, the torus is just this line. So the tangent space of the torus is just a line. So the two vectors will align again, but with a different time rate. This is a power law, and actually we have a prediction. This is t to the minus 2. So even in this case, for 2D maps, we still can differentiate quite easily between regular and chaotic motion. So just a small recap. The most important thing is, because I'm in general more interested in multidimensional systems, if we have a multidimensional system, the Sally goes exponentially fast to 0 for chaotic orbits, and it remains practically constant, fluctuates around some positive constant value for regular orbits, but the two values are they have very large differences, orders of magnitude. While in the case of the 2D maps, both of them, for both cases, Sally goes to 0, but with completely different time rates. Exponential decay for the chaotic orbits and power law decay for the regular orbits. Okay, so now, how can we use Lagrangian descriptors in order to quantify chaos and get some information about the chaoticity of regularity of orbits? So we have an n capital dimensional phase space, fine, and we can consider a subspace. Of course, we can consider the whole space. Let's say n small, a subspace. And then let's think of a line. And here we have our orbit, and we find some neighbors. We create a grid, and we have the first neighbors. This sigma is the distance between neighboring points in the grid. This I counts the directions, because you can have it in many directions. And this EI is the usual basis, 1, 0, 0, 0, 1, 1. So what I'm saying here, I have my point, and I find nearby points in the grid. If I just want to do it in a line, I have 2 points. If I want to do it on a plane, I have 4 points in 2 directions. If I want to go to much higher dimensions, you understand that. So here's this yi plus minus, left, right, or things like that, means that the first neighbors in each direction I in this grid. And then what I do is I create these two different quantities. The difference, which I call d, n is the dimensionality of the subspace where I'm working. So what I'm doing is I compute the Lagrangian descriptor for my orbit, for the first nearby point and the other nearby point, and compute this quantity. And in some sense, dividing by the value is just for scaling. Okay? So that's the difference. So I compute practically the mean of the differences of the Lagrangian descriptor between nearby points. And I compute something similar, but here is the ratio. I take the Lagrangian descriptor at my point and the nearby point and the other nearby point and create the ratio. So this is the ratio, this is the difference. That was our idea, to compute these quantities and see how they behave. Why? Let's see an example. Here I take, again, the Henon-Heil system. We have the regular orbit, and for the regular orbit, I compute both the ratios and the differences, and for another chaotic orbit, that thing, the same value. So here you see that the regular orbit, this is the difference, this is the ratio. They have very small values in log scale compared to the values that these quantities get for the chaotic orbits. So it seems, not it seems, it is actually a big difference between these two values. Why is this happening? So let's take again the Helmholtz and take the Lagrangian descriptor along these lines. You remember we did that in the Duffin oscillator, and we were able to find the cusp square which corresponds to the manifolds. So if you compute the Lagrangian descriptors along these lines, you get this plot. Actually, this was done in that paper, and that was one of the starting points of our investigation. And you see a correspondence here. When we are inside the island of stability, you have a smooth variation. Or here you have the other island. When you are inside the chaotic region, you have some erratic behavior of the values. So how can we quantify these differences? And that was the idea, to introduce these two quantities. So if you compute for a value of time 10 to the 3, 1,000 time units, we are computing the Lagrangian descriptor for 1,000 time units, and actually it is not necessary to go backwards and forwards in time. One direction is enough, so you're gaining computational time. So here we're computing only forward in time. And if we compute the difference and the ratio, you get these plots. And you can see again the correspondence. This region corresponds to this island, small values. This is log scale. Again, similar structure there. And higher values correspond to chaotic regions. It is not, unfortunately, that clear because, for example, what is happening here, here you see some large values. Here at the same region you see some small values. But the general tendency is large values chaos, small values regularity. And then if you draw some threshold line, of course here there is some flexibility how you define this threshold line, this or that for its quantity, then the orbits that they give you values above are chaotic, the others are regular. How do we estimate these threshold values? We actually created distribution of these numbers. And here you see the blue curve is the distribution of these points here. And you see two large peaks. Actually, you could understand that here we have an accumulation of points around 10 to the minus 2. And here we have accumulation of points around 10 to the minus 5. You see that. And we just find the minimum between these two peaks. And this is considered as a good estimation of a separation. So whatever is above this value is considered chaotic. What is below is considered regular. And if you see the same investigation for the Sally, and here I have two plots. Let's take first the 10 to the 6. 10 to the 6, it is a long time, but much longer than that. But the idea is the following. If you compute that, you will see that, and here you see that there are points either with very large Sally values or very small. Here is 10 to the minus 16. In between, there are a few points. Of course, if you do it for smaller times, the in-between points are more because they correspond to sticky orbits that you have to wait a little bit longer. But still, there is a clear distinction between high values, regular motion, 10 to the minus 16 of very small values, practically zero chaotic orbits. So since the Sally was designed in order to act as a chaos indicator, we will consider as the true nature of the orbits revealed by the Sally. So whenever we have Sally, we say this is the true nature of the orbit, regular or chaotic. And then we will compare this quantification with what we get from the Lagrangian descriptor quantities. And since we like color plots, we integrate orbits. We color them according to the Sally value, the logarithm, or the difference or ratio of the Lagrangian descriptors. And you see these plots, they look similar, which is a good sign. That means that all these things have meaning. But you remember I also mentioned here that some points are maybe not correctly classified. And this is true. Again, assuming that the Sally quantification is the correct one, here I plot the points on this region which are not correctly identified by the difference of the Lagrangian descriptors. These blue points are regular orbits in reality which were quantified as chaotic, and the red points are chaotic orbits in reality that, according to this criterion, were quantified as regular. And the same discrepancies are shown here for the ratio. This is not really very bad because the misclassified orbits are less than 10%. Actually, even this 10% is somehow the upper limit. Which, to be frank, this is a very good percentage because this computation is much faster than that and quite efficient and computationally easy. So we do a similar analysis for the 2D standard map. These are the values. We have some thresholds again from the distributions of the quantities, the ratios, and the differences. And again, the difference, the ratio, and the SALI give you the same picture. And if you see which orbits are misclassified, you see again that this misclassification is happening close to the borders. And of course, I have to remind you the time that we integrate here is a few orders of magnitude than the time here. So we integrate further in with SALI in order to reveal the true nature of the orbits in order to have a reference. But this is encouraging again, because we see that the main features are captured and they are there. And we also did some numerical analysis about how the different parameters in our computation is influencing the percentage of correctly characterized orbits. So let's see the main plots, not the insets. First, this is the difference and this is the ratio of the Lagrangian descriptors. And here, different colors correspond to different grid sizes. We start from 10 to the minus 3, this blue curve, up to 10 to the minus 4, the red curve. And this is the number of iterations of our mapping. And here we see what you would expect. If you have a finer grid, then you will get more correct information. And you see that the red curve is, in general, behaving better because 98% of the orbits were classified correctly. And the same is true here for the ratio. The red curve eventually is giving you higher values, which means that the finer grid is, of course, more accurate. But another thing that you see here is that if you integrate further in time for a good grid, for a fine grid, then eventually you reach some kind of plateau and you are not improving the percentage. And the percentage is 97 or 98%. So I told you before that in the worst case scenario, you have something like 90% accuracy, which means you just misclassified 10%, but that was actually the lower limit, because here I'm just integrating for 100 time units, and you see that I have a 90% accuracy. Same plot or same approach is done in the insets for the Henon-Heil system, and here we still see that as we go further in time, we're improving, but you have to keep in mind that although there's a big difference here. Here we go up to 10 to the 4 iterations of the map. So here we go up to 10 to the 3 time units, which is not the same, because if you integrate an orbit in the Henon-Heil system for 1,000 time units, you might have, I don't know, 10 crossing points or 20 crossing points. But here we are on the map and we are already on the Poincaré section, so we have many, many more points. That's why this region corresponds still practically to that region where things are still improving as we go further in time. And then there was another related quantity. Again, that was some kind of inspiration for us, because when we were starting working with that, we became aware of this paper here, where they propose something which looks like an estimation of the second derivative. So again, we have the Lagrangian descriptor of the orbit, the nearby orbits, and the grid spacing. And we see also for this quantity something similar. The distribution has these two peaks. If you take this threshold value in order to discriminate between large values, chaos, small values, regular motion, you can do that. You have similar plots, nice looking color plots. Again, some orbits are misclassified, and we generalize this kind of definition to higher dimensions. And again, this is working. And as a final example is, because as I said, in general, I'm more interested in going into multidimensional systems. Okay, four dimensions is not multi, but going further, because I would like to be able to see a value, not a distribution or a color plot, because in many dimensions that's problematic. By registering a value, I can say this is regular or this is chaotic. So here I have two standard maps that they are coupled. This beta is B is the coupling parameter. And just an example, I take two initial conditions, one regular, the blue point, one chaotic, and I'm projecting here on the x1, x2 plane. This is a four-dimensional space, and you see this kind of torus-like structure and chaotic behavior. If you compute the Lyapunov exponent, you see what you would expect. For the regular orbit, it goes to 0 with the slope more or less -1. Regular chaotic orbit remains constant, positive value. The SALI, again, you see that for the regular orbit, the SALI is large, 10 to the -2, while for the chaotic orbit, after 100 iterations, it went down to 10 to the -16, practically 0. And if we compute the difference, the ratio, and well, we do not have a name, let's say this quantity S, which is the second derivative, that's why we say S, you see again this behavior that for chaotic orbits we get higher values eventually, because you see at the initial times you might have some crossing, so you just need to give the indicator some time. And if we go further and have this kind of plots in a subspace, a slice of the four-dimensional space in order to visualize, you see again the distributions of the three different quantities, the difference ratio, second derivative, gives you this kind of two peaks. You can find more or less a threshold, and then using that you misclassify some orbits. But again, this is not as serious as it might look here. It is really even less than 10%. So these ideas show that we can use Lagrangian descriptors in order to get a more global understanding of dynamical systems, and eventually you can use them also to higher dimensions where you do not really need to have a visualization in order to find, let's say, if you're interested in that, what is the percentage of chaos in your system? How many initial conditions are chaotic and how many are leading to regular motion? And here based on these results, probably based on these ideas, I just give you the distributions of the different quantities in time. And here you see for the difference, for time 50 up to 2,500, more or less the distribution remains the same. Yeah, there are some differences. Again, for the ratio, the same thing. Here we have practically the same thing for the second derivative. The only thing is that this is shifting towards larger values, and the reason is because here we are not normalizing in some sense by dividing with the value of the Lagrangian descriptor. But more or less you have this behavior, and you can see the two peaks, chaos, regularity, and in between you can choose a threshold, of course with some kind of flexibility there. If you compute the same distribution for the Lyapunov exponent, what you would expect, you would expect the following. If I compute the Lyapunov exponent here, I have large value, small value. Here, the large value remains more or less the same at the same level. The small value for the regular orbit goes down because the Lyapunov exponent estimator decreases. So this is reflected on the fact that we have a big peak for the chaotic orbits, and then the peak for the regular orbits is moving to smaller and smaller values as you go further and further in time, which is, okay, what we would expect. One good thing about the SALI is that, as I said, very fast the orbits show their chaotic nature. They reach very small values, practical 0, 10 to the minus 16. Okay, you can consider as numerical 0, 10 to the minus 10 if you want, so that's even faster. While there might be some sticky orbits that you have to wait a little bit longer in order to see these small values. And this is reflected also in the distributions. You see that the distribution has, no matter what is your time, some peak for the regular orbits. And then for time 50, very small time, you see a big chunk of orbits with small Sally values. Actually, this is 10 to the minus 10 to the 10 to the minus 5. You wait a little bit longer, 100 time units, you see that this peak went even lower. And then after 250, practically all the chaotic orbits are there. So this is also a very good indication why this index is quite fast in distinguishing between regular and chaotic orbits. So yeah, just to summarize, I think that I don't have to go through that again. But the bottom line is that we can use Lagrangian descriptors to find a very good estimation of the overall chaotic behavior of a system. And the advantages with more accurate, if you want, numerical techniques is, first of all, is easy to compute. As I said, it is not necessary to go very long in time. It is not necessary to compute backward and forward in time, only forward in time. And the other really important thing is that you are computing only the orbits. You do not need, for this computation of the Lagrangian descriptor indicators, to compute the evolution of small deviations like you do when you have the Sally or the Lyapunov exponents. You do not need to integrate the variational equations. This is not a big problem in most simple-looking models, but in some cases, your dynamical system can be quite complicated, and even writing down the variational equations can be a problem. And here are a list of references. Blue are some basic references for Lagrangian descriptors. Most of the people that they are included, they are here in the audience. Some basic papers on the Sally method, and these two papers are the papers that my presentation was based, where we introduced these indicators based on the values of Lagrangian descriptors of nearby orbits. Thank you again for your attention, and Steve, happy birthday again, and let's hope in 10 years we will celebrate again.
Thank you very much. Are there some questions or remarks? Yes.
I was just wondering, this miscalculated percentage, so do you expect it to become higher with growing dimensions or lower?
Okay.
Let me set the reason I'm asking this question is, just from purely conservative Hamiltonian case, for example, if you just look at a 3 degree of freedom, you have the Arnold web, and then you have the Nekrashev stability that comes at the junctions, and if you go higher, the stability will become more and more near the junctions. There's different type of local chaotic things that can stick around these junctions, right? So that would seem to suggest that you would miscalculate more as you go, or because they would be trapped for different time scales.
Well, actually, we saw that the miscalculation happens at the borders of the stability islands. Now, the real question is, how, as we go to higher dimensions, do you have more stability islands or less stability islands? And the question is, are you close to the integrable system where the Nekrashev regime appears? Then there you will have more misclassifications. But if you are in multidimensional system, which is more chaotic, let's say, and you have the percentage of stability islands is not that big, then the miscalculated orbit should not be that big as a percentage, because most of the phase space will be chaotic. So what I'm saying is, the key point is, the borders of the islands are the problematic areas. So if your phase space has many islands, even in these systems, if I decrease the energy of the Henon-Hiles and I go to regions where I have more and more regular orbits, then it might increase also the points that are miscalculated. But I have not done that. I'm just thinking now.
Just one more quick question.
Yeah.
So the cutoff value that you were choosing was based on your distribution.
Yeah.
I saw that in the 2 degree of freedom, that was clear. You had 2 nice peaks, and there was a point. But in the 4D map that you were showing, the other peak was sort of really going away, right? So it was kind of maybe it
here,
can even
for
become
example,
flat, right?
Yeah, here, yeah. This is also. It is not only the dimensionality of the system; it depends also on the parameters of your system. In general, you have two peaks. They are not always that well defined. So here you see the 2 peaks are not that well defined with respect to here, for example. But this is not only an issue of dimensionality, it is also an issue of the parameters that you choose. So I could choose some other parameters here where I could have more distinct, but again, this is not something which is 100% clear. Actually, we have done another calculation. Here you see a zone where you could put this threshold. And we moved this threshold in that zone, and we saw that the misclassification is changed by 1 or 2%.
Right.
So what I'm saying, this is not a very, very accurate, but it is a good indication of the overall dynamics. If I tell you that practically 80% of your phase space is chaotic, in reality it might be 84%, but that's a good indication. It is not 60 or it is not 10. And you can get it quite easily and for free. This is a byproduct of computing the Lagrangian descriptors. If you want to have very accurate estimation of chaos, for example, or a classification of specific orbits, then you have to use something else, like SALI. I wouldn't say Lyapunov exponents because it is more time consuming. But if you want to get a general understanding of your system, or how a parameter, changing a parameter of the system, is it making more chaotic or not? If you compute the Lagrangian descriptors because you want to manifolds and other things, you can say, look, if I change this parameter, the chaos is increasing. This is true. Maybe the numbers are not 100% accurate, but the overall estimation is quite good. That's my main message.
Thank you.
Thanks.
Thank you. Yes.
Hi, Prof. So I'm just curious on the, you were obviously emphasizing that this is so much faster. Can I just get an idea of how much faster than SALI? Like orders of magnitude?
Yeah. So look, that's a good point. So here, what I was doing is I was computing these indicators up to 10 to the 3 time units, 1,000 time units. The classification, the correct classification of the SALI was done with 10 to the 6. Of course, I could do it also with 10 to the 3, but it will not be that. So from that point of view, I'm already computing things at least 2 orders of magnitude, not 3, because you have to compute some orbits also.
If you were to compute them for the same amount of time, is it still orders of magnitude faster? Like if I let the Lagrangian one run longer?
No, but actually, if I want to have the same time, what I will do is I will use the characterization of SALI here. But again, here you know that these orbits are chaotic orbits. They are sticky orbits. If you wait a little bit longer, they will go down. So this, if I stop at 10 to the 3, I will say that this orbit is regular, but actually it is not. So always, look, whatever computational technique you use, you always misclassify some orbits, even with a Lyapunov exponent, because there are always orbits at the borders. But the percentage is not that big.
Okay. But yeah, the variational equations adds a lot of time, always. Okay.
Always,
yeah, cool. Thank you.
Thanks.
No more questions. Thanks again to the speaker. Now we have the coffee break, and we will come back at 11. Okay, we will continue our morning session, and the next speaker, I think, is in the screen is Malcolm Hildebrand. Please, Malcolm, up to you.
Thank you.
Thank you very much.
Cool. So, good morning, everyone. And yes, thank you very much to the organizers for this wonderful conference and for letting me speak here and for allowing us to come together and celebrate Steve. So, thank you again, Steve, for everything you've done for so many of us and for how influential you've been. It's great to be able to come and celebrate together. So, you get a bit of a trifecta of these things, but I'm going to talk about something completely different to what Harris and Manthor spoke about earlier, but it's still going to have this caldera. So this is going to be our starring cast member. And hopefully by the end of this talk, you understand this picture with the help of this video. So we'll see how we go. And essentially, I'm going to be talking about this origin fate map. And it's going to be a story of how we can use very simple questions to delve into very complex problems. And so a bit like the Lagrangian descriptors to quantified chaos, this is kind of a philosophy which I'm quite fond of. How can we use simple building blocks to answer complex questions? And of course, this was another solo effort. And so first and foremost, I want to thank Harris, Steve, and Manthos. Manthos, you need to update your photograph somewhere. But these were the people who worked on this. And this was done in the group of Harris Korkos at the University of Cape Town before I moved to Dresden. So navigating phase space can be complicated. I'd like to say going from A to B can be harder than we think. When you're doing phase-space transport, you can't just plug it into Google Maps and ask, how do I get there? You have to do some hard work. And so maybe we've seen examples from fluid mechanics, from astronomy, from chemistry, anything where you want to go from one state to another, it's hard to understand sometimes. And so you get these beautifully complex pictures like this, and some very powerful methods, some of which Manthos discussed earlier, about how we can go about understanding these transport phenomena. And of course, Steve has a book on the topic because he has a book on everything. And he says this very well and says, by transport, I mean motion between regions describing qualitatively different types of motion in the phase space of some dynamical system. I think this sums it up very well. So we're trying to go from qualitatively different states. So by A and B, I mean qualitatively different ways of motion, or in sort of fluid, it could be different places in our physical box that we have our fluid flowing. In chemistry, it could be different configurations of our molecules, and so on. And so this harks back to what Eric spoke about yesterday with symbolic dynamics. And so when we're thinking about this, we really mean A and B can symbolize different regions of our phase space in the symbolic dynamic sense. And so that's something we're going to tap into. And then this you've already seen, our caldera. So I'm not going to go into detail because Manthos has explained it very nicely. But essentially, we have this guy here. We have some C1 to C2 and C3, which Manthos varied and showed us how that produced different bifurcations and different behaviors. Note here, lambda is our stretching parameter. So this will feature again today. And the main thing we need to care about is that we have two entrances. And so in the chemistry sense, this is where the reactants come from. And then two exits. And then the central minimum in the middle where the magic happens. And we can also take the unstretched one, and then we can stretch it like so, and we stretch it out, and this flattens nicely. And so this is then what Manthos spoke about before, when you have the breaking of dynamical matching. And so the stretching procedure is, let's say, the physical phenomenon, which we're going to investigate today. It's going to be our test case, our playground for understanding the origin fate map. So the simple question we're going to ask, has been made into a famous song. So you can always think about this: where do things come from, and where do they go, right? That's what we're trying to do, from A to B, from B to A. And so we can take two very similar initial conditions, see where it comes from, integrate this backward in time, right? That's how we understand going, where do we come from, and sweep. Okay, rendering in 3D is hard, but this red line is, of course, behind the caldera, and it exited through that top channel. And very similarly, we can do this again with a very, very nearby initial condition, and they both came from the same place. So if we integrate backwards in time, we get the same thing. Then we can ask, where did they go? And we can play the videos again, but now we're going forward in time. And so this guy goes forward, he comes to the exit. Sorry, sir, I need to see your ticket. He goes back, oscillates around, Ah, thank you, go through. And so now we have essentially this dynamical matching pattern, right? This is integrating forward to see where it goes. We can do the same thing now for the slightly different initial condition, and we'll ask, okay, with a slight tweak, what do we get? Does it go forward? Does it go backwards? Need your ticket, please, sir. Sorry. Sir, that's your metro ticket. That's not a party ticket. And boom, okay, screw it. I'm going to exit this way. Okay, and so we have two different cases. We ask the same questions. Where they come from, where they go. They came from the same place. They went to different places. Why? How? And the question you should be asking is, how did I choose these initial conditions? And that's what I'm going to answer in a second. So, qualitatively, we now need to put labels on these qualitatively different regions of phase space. And in the Caldera, it's relatively simple, because we have these two entrances and two exits. We call them entrances and exits. Of course, it's possible for trajectories to exit or enter from any of them. But since we have this slope on the Caldera, we can think of them as entrances and exits. And we just throw some labels on. So in a 2D contour plot of the same potential, we can label this entrance 1, this entrance 2, this exit 3, and this exit 4. Right? Again, nothing profound. We're just doing very simple things, asking where did they come from, where did they go, and how can I label them. And so with this, we can create essentially origin fate indices. So I can say something that goes from 2 to 4, 1 to 3, 2 to 3, right? All I'm doing is labeling these different regions of phase space from where did we come from and where did we go. So we can look at these examples. So what I just showed you before, we start at the top right, exit bottom left. So we go across the Caldera 2 to 4, right? Very simple, and I can do this easily by taking some initial condition, integrating backwards. That gives me my origin, integrating it forward, that gives me my fate. And then we can take the other case and find out where it ended, and that ended in 3, right? So we have 2 to 4 and 2 to 3. And so here you can see the configuration space projection of these trajectories. And this is nice. So now we're slowly becoming slightly more quantitative, slightly more firm and less woolly about what do we mean by come from and go. And so we can now say, okay, some given initial condition, I can find its origin, I can find its fate, and I can label it accordingly, which is great. So I can now start asking real questions. But of course, this is kind of not very exciting so far, because if I want an arbitrary initial condition, I can always integrate it backwards and forwards. But how do I actually start gaining information about the system? How do I start painting a picture of phase space transport? And so to do this, we're going to take a point array surface of section, similar to what Manthor did before. And so here we take a slice along the top of the Caldera. And so we get a whole bunch of trajectories, which we can then study. And on this point array surface, and okay, for convenience, I just take py to be positive to match what previous work did. You can take py to be negative. You can take a surface of your choice, as we will see just now. Now take the surface, and then instead of plotting something like the Lyapunov exponent or Sali, as we saw before, which you can also do, here we plot the origin fate indices. Okay? So let's take a moment to think about this picture, because there's a lot going on, but it's essentially very simple, and it's very direct. So for each point on the surface, we integrate forward to get our fate index, integrate backwards to get our origin index, and then we just assign a color to each of those indices, right? And so if you remember from 2 to 4 or 2 to 3, that's a particular behavior. And so then here on the color bar, we have each of these behaviors labeled. And so for every pair of origins and fates, we have a label. And then we get a bonus label because we integrate for a finite time. And so it's quite possible that for the finite time we choose, the trajectory never actually leaves the Caldera in either forward or backward time. And so then we get this extra purple color, which is in the middle, which is where we just have very, very long times spent in the center of the Caldera. Okay, and so here we can see some examples again of where we go, for example, from 4 to 2, right? Because now, of course, we have positive py, which means that most of our initial conditions are shooting up this way. If you took negative py, you'd have more things starting here and ending here. But since we're taking positive py, we end up with conditions that start at 4 and end at 2. And so that's this pink condition here, right? 4 to 2. So originates at 4, ends at 2. And we can take this red point, which starts at 4, loops around, and ends at 4. And this is perfectly possible. This is not a reactive trajectory. It's something that physically we're not super interested in, but they exist and we can label them. Great. So chemically interesting is dynamical matching. So this is what we heard at length from Manthos, so I'm not going to go into detail. All it means is, do we shoot straight across, or do we have some behavior where we go somewhere else? And so essentially we want to know, if I start at 2, do I always end at 4? Or if I start at 2, can I end at 3? And we know that if we stretch the caldera, this becomes possible. So another thing we can do is, of course, try and find this critical stretching, which we can do with manifolds. And we can also ask how many trajectories break this dynamical matching. So what proportion of our initial conditions that start from 2 end in 4 or end in 3, depending on how we stretch our caldera. Okay, so we take the same PSS. No worries, nothing's changed. And then we take the same PSS, stretch our caldera, and voila. Okay, nice, but still kind of confusing, right? So look at this big picture. We can see definite changes. We have now this massive region of trapped things and a mess of manifolds and so on going on. But what is interesting is that, okay, it does look like we have something starting to get close to intersecting here. And so this is what we saw before from Manthos of the invariant manifolds from the central minimum starting to intersect with manifolds from the upper right saddle. And so now, from a purely phenomenological direct route, we can see a signature of this occurring here as well. So to make this slightly easier to see, let's zoom in. And this is now the advantage of the method, right? Is all I'm doing is taking a grid of initial conditions, integrating forwards and backwards, which is on the scale of numerical simulations, basically free. And I can do this grid wherever I want, at whatever scale I want. And so now, instead of taking this big Poincare slice, I can zoom in on the region of interest. And so now I can say, okay, we take this guy here, blow it up, and I can make it as high resolution as I want by running more simulations. And now we see, aha, yes, there's clearly some intersection behavior here. And in particular, we have this light green color coming up. And this light green corresponds to 2 to 3. And if you remember, 2 to 3 was this slice around, which is the breaking of dynamical matching. We expect lots of 2 to 4. So all of this is 2 to 4, which is our dynamical matching behavior. But as we stretch the caldera, we enable this 2 to 3 behavior. Okay, so this is good. And this is very nice in that purely numerically, without having to ask too many questions about the underlying mechanics, I can get this. And so I do want to be clear that at this point, I'm not really explaining the mechanisms of the phase-space transport. I'm just exploring what happens and how we can understand this from a quantitative perspective. We will see later that combining this with manifolds becomes very powerful. But for now, I want to zoom in even further on what I care about. So I've identified this region as the region of interest in my PSS. But in this region of my PSS, there are a whole bunch of colors here which ain't appearing anywhere. And I don't care about those. I don't really care if I have a trajectory which starts at the top left and exits from the top left. In this case, what I want to ask about, the question I'm asking is, do I have dynamical matching from 2 to 4, or do I have broken dynamical matching from 2 into 3? And so by asking that question, I can just recolor things, scrap all of the unnecessary things, and then have a much simpler color bar. Right? So all of this stuff that I don't really care about, I just exclude, make it gray. And then I have right to right, broken dynamical matching, left to left, broken dynamical matching. Of course, on this surface, this doesn't appear, but it's a behavior that I'm interested in, so I don't want to exclude it a priori. Right to left, dynamical matching, and then left to right, dynamical matching. And so now, instead of this slightly messier picture, it gets increasingly clean and clear. And so we now have these yellow lobes, which correspond to the breaking of dynamical matching, and our big green splodge, which is the right to left dynamical matching. So here we've shown that, okay, simply numerically, I can vary lambda, I can plot this, and I can see, aha, at this lambda, I can detect that we have the breaking of dynamical matching. We have these 2 to 3 trajectories appearing. And so it's kind of a thing which we know from teaching and from generally presenting things, that we want to minimize redundant information. If I stand here and give you a long speech about Trafalgar Square, it distracts a lot from what I'm actually trying to tell you. So we want to remove distractions and just focus on the question we're trying to address. And so we can ask many different questions using the same data, but for each question, we should represent the data accordingly, and so that's what we do here. And this allows us exactly to confirm that we have broken dynamical matching. And then the great thing, and I think this is really where the origin of fate map shines, is that we can combine this with the computation of invariant manifolds. Because actually how this started is that I was working on this Caldera potential with Steve, Manthos, and Harrison. I was trying to understand, okay, we have all these lobes. We can calculate these manifolds using Lagrangian descriptors. So these black lines here are the manifolds from the Lagrangian descriptor computations. But then when I have this sort of nested structure here, how the heck do I tell which lobe is which? And so then the origin fate map takes these outlines of the manifolds and colors in each lobe for us. And so for me, this is kind of amazing that this now combines the deep beauty of the manifold theory, which actually tells us about mechanics, actually is very insightful and very robust mathematically and rigorously. And instead of having to individually go case by case and say, okay, we have 12 lobes, let me drop a pin here and see what color it is. Instead of having to identify each lobe individually, I can just do it all at once. And this gives, I don't know, I just really like this kind of picture and this idea of combining the naive direct numerical approach with the profound mathematical approach. And so this, I think, is very useful. And so once again, we can see some examples. And this is how I picked my initial conditions earlier, right? Is they're very, very nearby. They have vanishingly different x coordinates. They have the same px momentum. But because I know where these lobes are exactly, I could pick these even closer together. And this is really super sensitive, but I could tune in and zoom and just find literally either side of a manifold, and I can pick some initial conditions, and we get wildly different behavior. So manifolds show us the lobes. The origin fate map tells us which lobes are which. Okay, and then two cool things before I run out of time. So dividing surfaces, fortunately Manthos has introduced this as well. The idea that it's surface of no return. So every trajectory which starts from the top right, entrance 2, and crosses this periodic orbit cannot exit from the top right unless it does some long meander. So essentially, every reactive trajectory has to cross this dividing surface. So if I take this dividing surface, I know for sure that every trajectory that crosses this is reactive. So if I take a PSS on this dividing surface instead of just a straight line, I know that I catch every single reactive trajectory which starts from origin 2. And this is great because this now means I can quantify things. But first, let's have a look at how this actually appears. And so here, because I'm taking this periodic orbit dividing surface as my PSS, I have absolutely no interaction from the left, so I have nothing entering from the top left. And so I can really, once again, throw away even more information and just say, okay, now I really want to know about only trajectories which start from this top right saddle. And so I take 3 colors, excluded, right to left dynamical matching, right to right broken dynamical matching. So in the unstretched case, all we see is right to left dynamical matching. And so this is for the negative PY case. You can take the positive and the negative PY case to get the complete picture. And in fact, if you had better 3D plotting software, you can plot this periodic orbit dividing surface as a surface in 3D, which is quite beautiful. But what you want to do is stretch it. And so instead of looking at the periodic orbit, the PSS, and seeing intersection of manifolds, what we see on the periodic orbit dividing surface is actually we have an invasion on this dividing surface of other manifolds. And so we have this appearance of right-to-right broken dynamical matching as we stretch. And so this little tongue here corresponds precisely to the lobes that we saw before in the PSS. And so this is what we see. And yeah, so minimize distraction. And now we can actually compute, because if we take this PSS and we take its counterpart with positive PY, we get all possible reactive coordinates, trajectories, and we can quantify things. So if we take all the trajectories on this dividing surface, and we ask how many end up at the bottom left, how many end up at the bottom right, we can calculate this branching ratio of the fraction of broken dynamical matching cases. So how many of my initial conditions exit left, how many exit right. And this actually has some very, very cool behavior, which I'm not going to go into. But essentially, by stretching it, we get this really, really beautiful fractal cascade of lobes, which we can understand both from the manifolds and from the origin fate map. Like as you stretch it, at first the broken dynamical matching part grows. Then suddenly we have this invasion of the dynamical matching again, and this continues ad infinitum. Okay, and then 30 seconds on something which is very cool, very much an outlook, but I think it's very fun, is that we do this backwards and forward in time. We also integrate backwards and forwards in some control parameter. And so if you've ever studied hysteresis, you'll be very familiar with this, is that you integrate forward, integrate backwards, and you see how things differ. And so in my example here is simulation of an active fluid. And so we have some oscillating steady state in the fluid flow, which has this beautiful sort of dancing vortex. And so if we project this into some attractor, we have some, say, periodic orbit, some limit cycle. Great. And then maybe instead of asking about phase-space transport, we want to see, okay, how does this attractor change in the control parameter? So I can decrease my control parameter and then take this limit cycle and shrink it down and see, aha. As I decrease, it turns into a fixed point. So here we have some kind of Hopf bifurcation. Great. So I can then think of this as an origin state for my attractor. And I can integrate this forward and say, aha, there's some curious destabilization going on here. And I can say, okay, so this is now the fate of my attractor. So instead of integrating backwards and forwards in time, instead of taking a PSS in my phase space, I could take some sort of parameter space sweep and increasing the parameter space for different attractors, I could construct some sort of equivalent origin fate map for this. Okay, this is super quick and just super fun, but I'm out of time. So I'm going to end with saying the origin fate map is simple, it's beautiful, but it actually allows us to answer some very complex questions. And I think it's a really useful tool, and it's a very useful philosophy for thinking about these kinds of problems. Yeah, so here's the paper. And probably more importantly, here's the code. And I would really encourage you to go and play with this, because if people play with it and are interested, then I'll happily add more content and tutorials or whatever. But if no one uses it, then it's not really motivating. So if you want to play around with it, this should give you everything you need to get started. I think it's a useful thing. But yeah, happy birthday, Steve, and thanks all for your attention.
We have time for a quick question.
So since we're talking about fluids and reactions, they do have a temperature, and there is some motion because of the temperature. A different way of looking at it is when you have so much folding and stretching that those lobes get really close together with very filamentary kind of gaps. But the diffusion between those, I think there's some point where it's going to have a high enough temperature, or they're too thin that it's just a blend.
Yeah, for sure. So, I mean, in a practical state, in anything with noise or like an advection diffusion equation, you wouldn't have this clear transition, but you'd get this sort of fuzzy transition, right? And so as the lobe invades, like eventually, it's sort of like first order versus second order phase transition kind of idea, right? Where
the big gaps will still be there.
Yeah.
At some point, you have to imagine.
Yeah, so you'd have this jumping between the stable states. So you have this metastable state, and you jump between them as you sort of transition. But yeah, you get a blurrier version of the same thing.
Okay, so thank you again to the speaker. And we move to the next speaker, please.
It's complicated. Social media is a hard place, man.
Is it,
yeah, you take that.
yeah, this is the other. Okay, please.
Good day, everyone. My name is Henok. I'm at the final stage of my PhD at the University of Cape Town under the supervision of Professor Skokos. First of all, I would like to thank the organizers for giving me the opportunity to be here and present my work. It feels like I'm the only person who has yet to collaborate with Professor Wiggins. I hope that I add that right very soon. I didn't think already, so happy for 66 flips. Okay, this work is in collaboration with Professor Communis' group at the University of at National Technical University of Athens. The aim of the work is to compare and quantify magnetic and kinetic chaos in toroidal plasmas. I will explain what magnetic and kinetic chaos is very soon. Okay, that's it. I always struggle with this. My talk is organized as follows. I will start with the model, then I will briefly go through the chaotic detection techniques, which was explained much better earlier. I will give you the numerical results, and I will summarize. Okay, tokamak. When we say tokamak, it's basically a machine that uses a magnetic field to confine plasmas in this donut-shaped structure, which we call torus. Most engineers and fusion engineer scientists believe that it's the most promising magnetic confinement concept for future fusion power plant. In tokamaks, we have two components to confine the plasma. The first component is the toroidal field, which is generated from this coil, and the other one, which goes around the long way of the torus, and the other goes around the short way of the torus, which we call poloidal field. Okay, I think, yes. All right. Okay. The magnetic field line, basically, the magnetic fields can be treated as a trajectory or an orbit, and they can be expressed by the Hamiltonian equations. Here, psi p is the Hamiltonian equation, which is given by, as you can see here, where theta and zeta, the toroidal and the poloidal angles, and where psi and psi p are the toroidal and poloidal flux of the magnetic field. Here, alpha here, when alpha is 0, basically psi p becomes integrable, which is the constant equation of motions. But if alpha is non-zero, then the system breaks its integrability. And the equation of motion of this Hamiltonian is given by this equation, where Q is the essential or unimportant parameter, which is essentially the ratio of the number of toroidal turns to the number of poloidal turns. And the Hamiltonian follows the guiding center approximation, which simply describes the complex nature of the charged particle motions of the Hamiltonian, the magnetic field. Sorry, the equation of this magnetic field, the equation of the guiding center motion is given by this equation, where mu represents the magnetic momentum, and rho parallel represents the velocity component of parallel to the magnetic field. In our study, we are using the large aspect ratio, which is basically we are taking a small ratio of the large side of the torus to the small side of the torus, which is basically the cross-section area. It can be shown that for low energy particles, where the magnetic moment and the velocity component parallel approach to zero, the charged particle motions drift becomes negligible, and it closely follows the magnetic field lines. In other words, the equation here given, the guiding center motion, which I'm going to call kinetic moving forward, corresponds to the previous equation, which is the magnetic field line. That's the premise of our work. So in our work, we are interested in to compare the chaoticity of these basically Bose equations. Okay, the chaos detection techniques we use. Professor Harris explained it well, so I'll just go through it briefly. The maximum Lyapunov exponent is given by this limit, but in practice we use the finite time Lyapunov exponent. For regular orbit, this finite time Lyapunov exponent follows this power law to the power of -1. When it comes to chaotic orbits, it's positive, while the maximum Lyapunov exponent has been used for a long time to quantify chaos, but it's computationally expensive, especially when it comes to multidimensional systems or weakly chaotic orbits. So as a result, we are going to use the smaller alignment index method. I will give you an example in the following slide why it is faster compared to Lyapunov exponent. The smaller alignment index is defined as the area of the parallelogram formed by two unit deviation vectors. Apologies for my voice, starting from last slide that just went on. In order to compute the smaller alignment index, we follow the evolution of the orbit itself and two unit deviation vectors, which are perpendicular. For multidimensional systems, psi remains constant for regular orbits, while for chaotic orbits, the two deviation vectors eventually align. That means it will go to zero exponentially fast following the direction of the Lyapunov exponent. When it comes to 2D maps, as explained earlier by Professor Skokos, we will have the same property for chaotic orbits, but when it comes to regular orbit, psi goes to zero following the power law, which is in the power of -1. Okay, here I'm just giving you representative cases for the kinetic orbit, which is the second model. Here, the top one is the Poincare surface of section. The black curves represent regular orbits, and the three colored orbits here, the dotted pointers or scatter points represent chaotic orbits, and two borders of islands, this light blue borders of island and the red border of island, which is the zoomed in, is in the inset given here. They represent the chaotic orbits. On the left here, we can see that the evolution of Lyapunov exponent goes to zero following the slope, which is to the power of -1, is in log scale, it's -1. While for chaotic orbits, it eventually remains constant, except the red line. I will come back to that in a bit. While for psi, the evolution remains constant for the regular orbit, which is the black curve, while it exponentially goes to zero for the chaotic orbits. If we look at the red curve here, I put it in the inset, it's a weakly chaotic orbit, which needs more time to distinguish the true nature. As you can see here on the given time frame, it still follows this slope, so someone might think it is a regular orbit, but psi detects its true nature within the given time frame. So we can say that psi detects the true nature of this weakly chaotic orbit. Here I'm just presenting a Poincare surface of section for different orbits on zeta p zeta orbit. Plane. On the left here, I'm coloring each initial condition according to the Lyapunov exponent, and on the right, I'm coloring it based on the final value of Sally. As we can see here, Sally clearly identifies a more detailed nature of the behavior of the guiding center orbits compared to the maximum Lyapunov exponent. The reason is very simple. If you see the order of magnitude here, it is 2, but if you see for Sally, it's around 8. At the bottom here, we have where I'm coloring it, the Poincare of surface of section according to the time required for Sally to detect chaos. Here we are using 10 to the power of minus 8, and the yellow areas indicates when the Sally value is greater than the threshold. So here we can say that not only Sally detects the true nature of the chaotic orbit, it's also efficient because we can stop the integration once Sally goes to 0. For instance, if you see here around 10 to the power of 5, we can stop the integration, so it will save us time. Here, I'm just giving you a representative case for the first model, which is the magnetic field line. Again, even if it's fast to integrate using Lyapunov exponent, still Sally detects the chaotic orbit, which is the red curve here, very fast after around time 2, but here it remains constant after 3. Okay, so back to the main objective. We started to compare the chaoticity of the magnetic field line and the kinetic chaos. So here on the left, I'm starting by creating a Poincare surface of section for the magnetic field line. Here, the magnetic PSS is in zeta equal to 0, which is the poloidal angle. Here we have the theta psi surface. Here we are coloring each orbit according to the value of Sally. In general, the yellowish area represents regular orbit, and the dark blue area represents chaotic orbit. As you can see here, the chaos appears around the separatrices of the island chains, where the degree is somehow similar, which is quantified by the value of Sally. Now, to compare it with the kinetic chaos, we are considering this the computational considerations. We are taking a Q profile with 2 perturbation of normal modes, which are 3 to 5 to having equal amplitudes. We are taking 3 particles with different characteristics. For low energy, we are taking 2.6 eV. For thermal energy, which is an intermediate case, we are taking 2.0 keV, and we are taking energetic, which is 3.3. Here on the top, you see the PSS of the low energy particle, where again the chaos appears around the separatrices here. So we can confirm that the magnetic PSS and the low energy particle, they correspond to each other, or in other words, chaos appears at the same radial position in both cases, as you can see, 0.6, 0.6 for instance. When we increase the energy, or for the thermal case, the kinetic chaos around the upper primary resonant, it extends, and as you can see here. And finally, for the energetic particle, the kinetic PSS has less chaotic, and the resonance appear in a quite different position due to large drifts across the magnetic field lines. here, don't stress about the details, the curves. The takeaway here is we could use SALI to have a global overview of the GC Hamiltonian. For instance, if we take this purple red line, if we take this purple red line here, for instance, it corresponds to the Poincare surface of the thermal particle case. For instance, if you see here greater than 0.4, we have an extended chaos, which is represented here on the wide chaotic region. And if we see this small strip, for instance, it just corresponds to these small islands which exist around the separatrists of the island chains. So to summarize, low energy particles closely follow the magnetic field line and exhibit similar chaoticity. High energy particles undergo large draft across magnetic field line, and SALI provides or offers us to identify and quantify chaos, for instance, in this case, in toroidal plasma models. And also we can use this constant of motion. I should have mentioned it, the last figure, the constant of motion. Basically, we are using energy p zeta where mu is constant. More details can be found in this paper, and I thank you very much.
Thank you very much. We will skip the session the question session because we are not enough time, so you can ask the speaker during the lunch. So the next speaker is Makina Gioglu.
How do we... Where? Control L, of course. Okay. So I can start. I have 15 minutes. All right. So first of all, thank you, Steve, for being here. And thank you all for being here. So I will be really, really short. I should be really, really short. So I will talk about the method of Lagrangian descriptors, something that you have never heard in this conference, and answer decodification. So, well, my plan was in the first part of the talk to give some basic ideas, but something like what is the phase space, what is the method of Lagrangian descriptors, that you have already, I think, heard of it 5 times already today. So, and then I will present one example that is one of the latest works with Steve and Anna and Guillermo. So, just to say it, what is a phase space? It's a geometric way to look into the solutions of a system of differential equations. Who was first to introduce that was Poincare in the context of celestial mechanics. And by this geometrical way, we can see how the phase space is divided into regions where trajectories have different qualitative behavior. Excellent. This will help us to understand the transport in geophysical flows, as the example that I will present, in chemical reaction dynamics, as Mattheos has presented, and all the students of Harry as well. So the method of Lagrangian descriptors, you all know. Scalar trajectory diagnostic. If we integrate forwards in time, it gives us the stable manifolds. If we integrate backwards in time, it gives us the unstable manifolds. The original definition, it is given by Anna, that is here, one of the organizers, in Madrid in 2009 in the Journal of Chaos. So I will skip the details, you already know. So this example, it is with, as I said, with Steve, Anna, and Guillermo, that he gave one talk yesterday. He's the CTO for Digital Air Solutions. So what we were trying to do in this example was to propose a new uncertainty measure that is appropriate to quantify the performance of different models in assessing the origin of a problem. Okay, and then what we found was that in the neighborhood of this observation, this uncertainty is really related to invariant manifolds. So, and we implement that in a real oil spill event that happened in the Eastern Mediterranean in 2021. Basically, this work, it comes to complete another work of Steve, Anna, and Guillermo that they have already done a year before our paper, and they presented this uncertainty quantification there. So just to show you what is the definition of this uncertainty quantification, this time backwards in time. So here with x1 capital, we can see that it represents the neighborhood around the observation, that is x1 small. And of course, we care about 2 dimensions. And then the target, the coordinates of the target is x1 asterisk, x2 asterisk. So what happened is, so at the beginning of 2021, they were reported by authorities that many tons of tars have approached many coastlines here and here. Here's the Eastern Mediterranean, here's Jordan, for example. And there was no reported accident. So where's the origin of the accident? So by combining satellite images and all these tools, they could find the origin of the accidents. For example, the origin of what happened in this orange coastline was what is inside the A box here. So 25 of January 2021, one accident happened here, and then after a few days it traveled into the region. You cannot really see can you see it? Can you see the point there? No. All right, so it started here. After a few days, we can see its evolution here, and then it hit it, I think, in less than 1 week, this coastline. And then the same happened in the green area here. So everything started here in the D area. After a few days, it traveled into the E box, let's say. It evolved, and then after 4 days, it hit the coastline. So how we can verify everything? We use this Lagrangian uncertainty quantification backwards in time, because now we know the result and we want to see where is the origin. Okay, so we go backwards in time. So just to say, just really fast, we know that the spill is following fluid partial trajectories, that they obey these kind of equations. Okay, so the position of the fluid partial at the surface of the ocean is given in longitude, latitude. R here is the Earth radius. And of course, what we do is we take these equations for different data sets. Actually, for 2 data sets, Guillermo yesterday mentioned about the global ocean model and the Mediterranean model as well. So we use these 2 data sets. We implement them into the Lagrangian uncertainty quantification backwards in time. And yes, and then what we know is that these kind of models, like the one that I saw before, possess a transport signature that is based on invariant manifolds. And then, that is based on the idea of Poincaré, obviously. And then we know that in the context of geophysical flows, these structures is what we call Lagrangian coherent structures. And how do we calculate them? We use the method of Lagrangian descriptors. So the results are the following. So if we consider this area here, the orange one, and the target backwards in time, the area A, and then again, what happens in the F area as a target, the area D, and we implement the Lagrangian uncertainty quantification backwards in time and the Lagrangian descriptors, for the green area, what we get is, so stay with me, the first column is the outcome of the Lagrangian uncertainty quantification backwards in time. In the second one is the Lagrangian descriptors. Well, it is the unstable manifolds. And in the first line is for the global ocean model. In the second line is for the Mediterranean model. So if we see this, the first conclusion that comes into our minds is that what happens in the neighborhood of the observation, which data set is performing better for this type of oil spill event. We can see that the error in here is smaller, so we can understand, at least for this kind of event, for this case, that it's performing better, the first data set, it's a global model. Then the other conclusion that we can see that is pretty impressive for me is that how beautifully aligned are the structures that we are getting from the unstable, the Lagrangian and uncertain codificator with the Lagrangian descriptors. We can see how aligned are these structures, and it's quite impressive. The same happens for both data sets, but at least in this case, we can see that the first one is behaving better for this type of accident. Then the same, we repeat the same for the orange region, that is this one here. And we consider as a target backwards in time this area. Again, we implement the two methods. So we can see first for the global ocean model, second for the Mediterranean model, and then first column again is the uncertainty codification, second column is the Lagrangian descriptors. What happens in the neighborhood of the observation is using the first model, this is the first one, the error is smaller, so we can see that it is behaving better. And then again, we can see how the structures that we are getting for the uncertainty codification are really related to the unstable manifolds. Again, yes, the first model is working better in this case. But then there is another question. What if we consider that the target, for example, to what happened in this coastline is not A, in fact this is a target, but it is its evolution here. So we consider closer targets. The same, what if for what happened in the F green area here, instead of considering as a target the D area, we consider its evolution, that is E. So closer targets. Again, we implement the Lagrangian uncertainty codification. And here, it is using the global model here. In the second column is it's not working, it is a Mediterranean model. For the green coastline, for the orange one, well, here we can see that the Mediterranean model, for example, in this case, it's performing better. So what are the conclusions? The main conclusions of this work are that, first of all, the structures that we are getting from the uncertainty codification backwards in time are related to the unstable manifolds, and we verify that using this example, the oil spill event that happened in the Mediterranean, Eastern Mediterranean. And then the other one is, okay, we have two data sets, which one is performing better for this kind of events? So we saw that when the targets are further, the global ocean model is performing better. But if we consider closer targets, in that case, well, we have seen that the Mediterranean also is performing quite well. So yes, so if you want more details, you can find them in this paper that we published with Anna and Stephen Guillermo in Físicas D. And of course, if you have more questions, you can email me. And obviously, I wanted to include this picture here. So first of all, Steve, I will be always and forever grateful for all the opportunities that you gave me, all the things I learned from you. So this photo has been taken the day that we wrote our first book. So this is the CHAMPS, it was part of the CHAMPS project with all the people there. I can see Mateos and Fran somewhere. Yes, I can see you. So it was an incredible experience. It was crazy because Steve had the idea to write a book in 2 days. So I was like, how this is possible? But we did it, and we had great time. I will never forget the things I learned there. It was an amazing experience. And for sure, me and Mateos, we will never forget the buffet that it was there eating these 2 days. Thank you very much for everything. I wouldn't be here if it wasn't you, and I will be grateful forever. Thank you. Happy birthday.
Thank you very much, Martina. So,
all right,
quick.
Go for it.
Will the talks from this conference be posted somewhere?
Sorry.
Will the talks from this
as an
conference?
organizer, I will reply. I guess, on YouTube. About the slides. Probably we
webpage.
can do that. Yeah, we can share them. Yes, as an organizer. Yeah, no,
Yes,
it's
yes,
amazing
sure.
to have them all together, and I guess we can do that, right? Perfect. Okay. Excellent.
Okay, so thanks again, Macrina.
You're
So
very
we'll
welcome.
move to the next speaker. Okay, Dimitris.
I have updated your slides. Okay. But make sure that it's the.
Yeah, in the.
I think if it is not here. Check if.
Maybe
Yes,
this
it's
one.
this one. Yes.
This one.
Check if it is.
Control level, yeah, okay. So this is the next speaker is Dimitris Giannakis, and you can read the title on the screen. And please, Dimitris, up to you.
Yeah, thank you very much for having me. Thank you for organizing this exciting event. I guess I'm the second speaker of the day that hasn't yet collaborated with Steve, but nonetheless it's great to be here to celebrate your 65th birthday. Best wishes. So I'll be talking about connections between Koopman and transfer operator methods and quantum mechanics. And to start off, first of all, let me also take this high-tech equipment and thank Nan for providing it. To start off, I'd like to show an excerpt from a paper of Richard Feynman, which in many ways ushered in the era of quantum computing. So in this paper, Feynman asks, given that nature is quantum mechanical, what sort of computer should we be using to simulate it? And he argued that computers, because they are themselves physical systems, should be like nature. In other words, they should be quantum mechanical themselves. And this was offered as a way of addressing certain computational bottleneck when it comes to simulating many-body quantum systems. So on classical computers, the computation cost grows exponentially with the number of particles, whereas if you were to simulate it quantum mechanically, you might be able to use like a polynomial number of quantum mechanical degrees of freedom. And so this paradigm is very strongly pursued these days, as both on the theoretical and hardware side. But the question I would like to discuss today is kind of like the converse of this. In other words, is simulating whether we could use quantum systems to simulate classical systems. So after all, classical dynamics governs a very broad range of phenomena, so that is an interesting question as well. It is, however, a somewhat challenging question because whereas quantum mechanics proceeds by unitary linear transformations of the state, I will be talking about that in more detail later on, classical dynamics, as we've heard in many talks today, are strongly nonlinear. So the question of how do you encode a classical dynamical system in the form of a quantum algorithm is highly non-trivial. Nonetheless, there have been quite active research on this topic in the last couple of decades. At least here I'm showing just a few examples of works that have been in the literature, and I will be talking about some general ideas that connect with the theory of Koopman and transfer operators. So the main theoretical tools that we're going to be using are operator methods for dynamical systems, where the focus of these frameworks are on the action of dynamics on spaces of observables. So observables will be things that we can measure about from a dynamical system there, and they will form linear spaces of functions. And I will be more precise about the choice of this function space. But given an appropriate such choice, there are two main families of operators that are relevant here. The first is the composition operator, or the Koopman operator as is now known, which basically takes functions and composes them with the dynamical flow. So it takes observables to observables. Essentially, it says that given a function, we're going to create a new function that evaluates the input function into the point at the point which is reached by the dynamics after evolution for time t. And that's a linear transformation on the space of functions. And the transfer operator is like a dual to the Koopman operator that describes how a dynamical system acts on measures. So this is important from a statistical and probabilistic description of dynamics. So this has been sort of like a foundational toolkit in ergodic theory, essentially since the 1930s from an analytical point of view. But in recent years, there have been considerable interest in the development of data-driven methods that are based around this framework, now that we have computational tools, and also in particular with recent developments in areas like machine learning to approximate this type of operators. I apologize, the colors are not really coming out here. Hopefully the references, the slides will be available online as well. So, however, what I would like to focus on today is the connection between this framework and another highly successful branch of modern science, namely quantum theory. Maybe I'll take a second to ask the audience if people are familiar to some extent with quantum mechanics by raise of hand. Okay, so there are some familiarity, but if you haven't seen that before, you're in luck. This is my one summary crash course, one slide crash course of what would normally be a 2-semester course in a university. But from a mathematical point of view, at least, quantum mechanics shares a lot of common structures with classical statistics, where you replace objects that are typically represented as functions with operators. So in particular, the state of a quantum system is a so-called density operator. So that's an operator that acts on a Hilbert space. So the Hilbert space here has to be chosen depending on the system. We'll be saying more about that. But given an appropriate choice of a Hilbert space, a density operator is a positive operator that has trace class operator that has trace equal to 1. And you can think of this in analogy with a probability density from classical statistics, which is a function which is integrable, the analog of trace class. It's positive, and the analog of a positive operator, and has integral equal to 1. So that's your kind of like operator version of a probability density. Observables in quantum mechanics are again operators. They are self-adjoint operators acting on the Hilbert space, which are these are to be thought in analogy with real valued random variables. Reality here being the analog of self-adjointness. And given that we have states and observables, quantum theory gives us rules for computing expectation values of observables, measurements of the system given the quantum state. This is by this formula here that computes the trace of the density operator times the observable. And you can think of this again in analogy as integrating against a probability density to compute the expectation value of a function. We also have a formula for computing probabilities of events to occur. So here, by omega, we are taking a subset of the real line, and we're computing the quantum expectation of this operator E of omega. So what is E of omega? E of omega is a projection operator that depends on omega. You can think of this in analogy with a characteristic function representing an event in classical statistics. We can compute probabilities as expectation values of characteristic functions. And in quantum mechanics, the characteristic functions are going to be replaced by these projections that we obtain from a spectral measure or spectral decomposition of a given operator. Evolution in quantum mechanics proceeds unitarily with unitary operators that act by conjugation on the quantum states. This is analogous to the picture that we had with the transfer operator, which is or like the push-forward map on probability measures. Here it's the action on quantum states. And when we measure the system, there is an analog of the Bayes rule that we have from classical statistics that allows us to condition the state. So this formula here may not look very similar to Bayes' formula. So let me just give a couple of remarks. So E here is an operator known sometimes as a quantum effect. This is the analog of an event again. An operator that is bounded by the zero operator and the identity operator, kind of like when you have a characteristic function. Again, it's a function that is bounded between 0 and 1. You can think of it that way. And if you were able to commute this operator, so the composition of operators being non-commutative, it's not possible, but you could move over the square root here, and it would become E, and then that starts to look more like a Bayesian update, that you multiply a probability density by a characteristic function to obtain the conditional density, and you have a normalization factor. So these are these basic axioms, and our goal is to use this framework to study different problems in modeling of classical dynamics. I will be talking about data simulation as an example, and some applications to developing quantum algorithms for simulating classical systems. Maybe I'll take a quick pause if there are any questions on this. Quick questions before I continue. Okay. All right. So moving on, let's go first through a high-level overview of how this procedure might work. So we're going to start from a classical dynamical system that has some state space X, and we're going to create a sequence of embeddings of that system to arrive at an equivalent quantum system. So the first is kind of familiar from the transfer operator approach to studying the statistical behavior of dynamics. Well, we can take points in the state space and embed them in spaces of probability measures over the state space. There is a natural way of doing this by basically taking points and mapping them onto Dirac delta measures. This is a perfectly well-defined continuous operation on the state space. And over here, we have the transfer operator that allows us to evolve probability measures under the dynamics. And it does so in a consistent manner, so in the sense of this diagram here, commuting, meaning that we could first embed and then dynamically evolve with the transfer operator, or evolve at the level of the state space and then map into probability measures, and we arrive at the same point. Of course, this is a much bigger space. There are many more, in some sense. This is a injective map, so we're putting our system, embedding in our system in a larger statistical space. But for us, this is going to be effectively the starting point into now develop quantum descriptions. So the next step will be to take probability measures, which live here, and we want to map them into quantum states. So here, H is a Hilbert space that we're going to have to choose for our dynamics. Q of H represents the set of all quantum states, or these density operators. And we're going to have to come up with a map that performs this embedding, and also with an evolution operator that acts on quantum states that makes this part of the diagram commute. So in essence, going through these steps, we have a for all purposes, equivalent description of our dynamical system acting at the level of quantum states. This will typically be an infinite dimensional system, but when we want to arrive at practical algorithms, we have to project that system into finite dimensions to get to this, what I call here, quantum computational level. So what is Bn here? So Bn is a Hilbert space, finite dimensional Hilbert space, that corresponds to a quantum computer that has n qubits, quantum computational bits. I will say a little bit more about that as we go along. So this is a space that has dimension 2 to the power n, basically. And we're going to map into quantum states of this Hilbert space. The goal here is to devise a mapping that ideally would make this diagram commute. We will see whether or not we can succeed with that. But perhaps more importantly, we would like that when we project the system, there is an evolution we can describe at the level of qubits. So this is a quantum algorithm that can be implemented using a modest number of quantum resources. We want to have a fast running time of this quantum algorithm. So this is the goal, and this is basically what our work has been for the last few years on this topic. I'll just to put here these two key points. The first point I want to make is that this general approach of looking at basically dynamics in this language of operators, so which has this non-commutative structure, allows for designing structure-preserving approximations, provides a flexible framework for designing structure-preserving approximations, which otherwise would be not as easily done with classical methods. So even if these methods are implemented using classical numerical computing, so they would be sort of like quantum-inspired methods, I would argue that they have some benefits. So we will talk about this property of positivity preservation later on. And at least in some cases, these methods are amenable to simulation using quantum circuits, so basically implementing this on a quantum computer that can be efficient. Okay, so I will give a few examples along these lines. The first will be about formulation of data simulation in this quantum mechanical language. These are my collaborators in this project. Dave and Brian are PhD students at math department at Dartmouth. So, we heard yesterday already some very nice discussion, the talks around data simulation already from Nan's talks in the morning. This appeared, so I'm kind of lucky in that regard. I probably won't do such a good job as explaining the general picture, but the goal in data simulation is that we want to estimate the state or observables of some dynamical system of which we have only partial knowledge of the state. And we update this knowledge by in a sequential approach where we make a forecast of our current state of knowledge, and we make a measurement in the future condition that will be our prior distribution to get a posterior distribution after a measurement that would ideally provide a more refined knowledge of the state or other observables of the system, and we keep iterating that procedure forward in time. So here we're going to do something similar, where we imagine again that we have our forward model that is able to advance probability densities classically. This would be the transfer operator from a mathematical point of view. We're going to assume here, I guess, without wanting to go too much into technicalities, that we have a measure-preserving flow. It has an invariant probability measure, and for the purposes of data simulation, it is natural to consider probability measures that are absolutely continuous with respect to the invariant measure of the system. So this is going to be our space of measures where the transfer operator acts, and observables are going to be essentially bounded functions with respect to that measure. And this forms an algebra of classical observables. It is a commutative algebra because we can multiply functions together in this space in a commutative manner. And we're going to embed this into a non-commutative operator algebra. Right? And given such a setup, we have a natural unitary operator because in a Hilbert space, namely L2 with respect to the invariant measure, and the Koopman operator that acts on it unitarily. So we have basically the main ingredients to implement these quantum systems, the axioms basically that I was showing earlier. But what we have to do is to define basically a map that embeds probability densities into quantum states or density operators. And one way of doing that is to basically say, take a probability density, I'm calling it here nu. So what's a probability density? It's a positive function in L1 that integrates to 1. Well, its square root if you take the root of a probability density, it's an element, it's a square integrable function now, so it's an element of L2. It's a unit vector in L2, and we're going to define a density operator that essentially projects along this vector. In quantum mechanics, the square root of the probability density here would be called a wave function. And this density operator that has rank 1 as an operator is an example of a so-called pure quantum state. Not every quantum state is of this form, but this is the recipe we're going to use for our embedding. Now, we can do something similar for observables. So we have observables which are L infinity functions, and there is a natural way to map them into bounded operators on the Hilbert space that correspond to multiplication operators. So if we take a bounded function f, we can create out of it an operator pi of f, which acts on elements g of the Hilbert space by multiplying them by f. And this is a bounded operator. It is self-adjoint when f is a real valued function, so it constitutes a quantum observable. And at the level of algebras, this is a representation of this commutative C-star algebra for technical jargon into these bounded operators on the Hilbert space. And given that we have our Koopman operator, we can define this unitary evolution of the quantum state. And the important part here is that we have the consistency between classical and quantum description. In other words, we can either evaluate classically expectation values of observables pushed forward under the transfer operator, with densities pushed forward under the transfer operator. This would be the forecast step in data assimilation. Or we can do the same procedure, the analogous procedure, quantum mechanically. We get to the same result. Now, again, to have computational algorithms, we have to project down to finite dimensions. And for that, we're going to need to choose some finite dimensional subspace of our Hilbert space. And we go essentially from density operators to density matrices in doing so. And the convergence of these algorithms is to be understood as a limit where you allow, these spaces, these approximation spaces, to increase to the entire Hilbert space. And the one point I want to make about this procedure, that it's automatically positivity preserving. Namely, if you take an operator which is positive, like a quantum state, and you project it in this way by conjugation, you automatically get a positive operator. However, at the level of functions, if you do an orthogonal projection of a positive function, let's say a probability density, you don't necessarily get a positive function out of it. Like you can have Gibbs oscillations, for instance, that break positivity. And this is one example where passing through this level of this infinite dimensional quantum system basically gives us a nice flexible arena to design this type of structure preserving approximations in ways that would be at least non-trivial to do classically, or not possible with the same tools using orthogonal projections. And this holds independently of whether these algorithms are implemented on quantum computers. In fact, the example that I will show you in a second will be just implemented classically. But this is like a snapshot of how this data simulation algorithm operates. Essentially, it mirrors the forecast analysis cycle of a classical data simulation that we heard yesterday in non-stocks, for example, where with the extra ingredient here that we need to update our quantum state at observations by this Bayesian rule, the quantum version of Bayesian rule. I'm happy to talk about this offline, how we do this. We use some methods, kernel-based approaches that allow us to create an approximation, essentially, of the Bayesian update that I described earlier. But this is how the procedure works in a nutshell. And also, without wanting to too much to go into the details, there is just want to show you that there is a data-driven implementation of this procedure that uses the same kind of tools that one might use for dynamic mode decomposition or extended dynamic mode decomposition of Koopman operators. It basically involves representing all linear operators involved by matrices in a basis. And the basis here, we build it rather carefully to be an orthonormal basis of our Hilbert space associated with the invariant measure. I'm happy to talk about this more later on. So there is one example I wanted to show here is the data simulation of the El Nino phenomenon. So this is we did this in the context of a climate model, so CCSM4. I believe this was also mentioned yesterday, if I'm not mistaken, where we took a long integration of this model and we used about 1,000 years as training data. And by training here, I mean observations of Indo-Pacific sea surface temperature field from the model. And the goal is to assimilate this data and make predictions of an observable, which is the Nino 3.4 index. So it's like making a prediction of El Nino in this model. So, these panels here show running forecast made from this method by essentially computing empirical probability distributions, or the mean, from the quantum state using the formulas that I showed in the beginning of the talk. The x-axis here is the the verification time of the forecast. And as we go down, the lead time increases in the panels. The black line shows the red line here shows the truth. The black line is the mean forecast obtained from the quantum state, and colors here correspond to probability, logarithms of probability density. And so you can see basically that as we increase the lead time, the uncertainty increases, as you might expect for a potentially chaotic phenomenon like El Nino, but it does in a way that is broadly consistent with a true signal. So we have some relatively favorable forecast skill for obtained with this method. Okay, so and now we're basically working on testing this also in the context of reanalysis data, so making predictions of actual El Nino events in nature. So now, so far, I talked about this data simulation as an example of a quantum-inspired algorithm, meaning we took the ideas of quantum mechanics to come up with a formulation of data simulation that we run on a classical computer. Now, I'd like to switch gears somewhat and talk about a project where we actually try to implement a quantum simulation algorithm on a real quantum computer. So these are my collaborators here on this work, and we're going to start from a relatively simple class of dynamical systems, and then I will try to generalize this in the last part of the talk. So, but before I specify the class of system in questions, so now we're focusing here on this step where let's say we produce this infinite dimensional quantum system that is an exact copy, like a true embedding of our classical system. But now we want to project it into finite dimensions, taking into account specifically that the Hilbert space that we are projecting onto is associated with a quantum computer. And by that, I mean that we have a space that is a tensor product of two-dimensional complex Hilbert spaces, each one of them is being associated with a quantum computational bit. So this space here has dimension 2 to the power n, so it's an exponentially large dimensional Hilbert space in the number of qubits. It has a canonical basis that we can choose it as an eigenbasis of this so-called Pauli Z operator, and we're going to index the basis elements in this Dirac ket notation with either 0 or 1. And correspondingly, if we want to describe a basis for the tensor product Hilbert space, which is basically the entire quantum computer, we can specify the basis elements as a binary string of length n. So a projection here, like if we want to go from the infinite dimensional quantum system to the quantum computer, will basically can be implemented by assigning to different basis element of the Hilbert space a given binary string that will map them into one of these quantum computational basis vectors. And we want to do this in a way that makes this evolution here efficiently implementable using quantum logic gates. That's the goal. Okay, so the example of dynamics that we're going to use is going to be a highly structured system. It's not going to be a chaotic system. I will be talking about that, hopefully, at the last part of the talk. We're going to consider that we have an irrational rotation system on a torus of dimension d. So it's parameterized by d frequency parameters, which are rationally independent and has this analytically solvable evolution map. And I should say that this is not, we're not making a requirement that the system that we're actually analyzing, meaning the differential equations, are of this form, but we're asking that the system is equivalent to such a prototype system under a conjugacy, if you wish. So there are ways to, if you have a general ergodic system that has pure point spectrum, to transform it into an equivalent system of this form, if it's in continuous time. So I'm going to assume this structure for the purpose of developing or describing the algorithm. Okay, so well, we have to choose. If we want to design a quantum system on this torus, we have to first choose a Hilbert space for the torus. And because here our goal is to make point-wise predictions, and in L2 you don't have point-wise evaluation, we're going to choose our function, our space, to be a so-called reproducing kernel Hilbert space of functions. These are spaces which have well-defined point-wise evaluation. And being on the torus, we can use tools from Fourier analysis to build these reproducing kernel Hilbert spaces, basically by writing down a kernel with this Mercer sum, using the Fourier functions of the torus on the torus as a basis. We want to do this in a way that makes our RKHS, as a reproducing kernel Hilbert space, to have extra structure. Namely, we want it to be closed under point-wise multiplication of functions. So a general reproducing kernel Hilbert space doesn't have that property. If you take two functions in an RKHS, you multiply them together, the result is not necessarily an element of the RKHS. But for this choice of kernels here, what we've shown in previous work, that this is in fact closed, and it forms an example of a commutative Banach algebra, in the sense that point-wise multiplication satisfies a bound of this form. And there are, this choice of spaces here connects with other work in harmonic analysis that is closely related. It is important to have this structure because, remember, we're representing classical observables by multiplication operators on a Hilbert space, and having this property is highly beneficial for our purpose. Okay, but given that we've made this choice, for any reproducing kernel Hilbert space, there's a well-defined point-wise evaluation that is a continuous function that expressible as an inner product. And we also have a canonical way of building orthonormal basis for our RKHS by scaling Fourier functions by these coefficients here that depend on these constants, lambda. Okay. So with that, we can talk about Koopman operators on this RKHS. For this class of dynamics, the Koopman operators act unitarily on our chosen RKHS, and they have an infinitesimal generator. So this is like a directional derivative on functions. You can think of it as somehow like a v dot grad type of operator, where v would be the vector field of the dynamics, and there is an eigendecomposition of the generator. So it's, in this case, the operator is actually diagonalizable. It has this pure point spectrum property that it has an orthonormal basis of eigenfunctions, where the eigenvalues correspond to eigenfrequencies of the dynamical system, and they have this important group structure. Namely, the sum of two eigenvalues is again an eigenvalue, and the product of two eigenfunctions is an eigenfunction up to some proportionality constant. This, I should say, is sort of highly atypical for general dynamical system, but this is the structure that we're exploiting here for these algorithms that we would like to generalize later on. Okay. So with that, what we did, and I don't have time to go through the details of this construction, in our work is to basically implement a mapping from this RKHS into the space of n qubits, in which when we project our generator, we end up with a quantum mechanical Hamiltonian. I'm writing it here as h multiplied by a factor of I, because in quantum mechanics, conventionally, the generator of dynamics is taken to be self-adjoint, whereas V is a skew-adjoint operator. So here we have a quantum mechanical Hamiltonian that results from this projection that has this property of being expressible in a sum of commuting operators which are given by tensor products of these Pauli Z operators that were shown earlier with identity operators. And this is a very nice structure from the point of view of implementing in a quantum circuit, because if you exponentiate this Hamiltonian, this will give you the unitary evolution operator, so basically running the algorithm forward in time. You can basically factorize this evolution into a tensor product of individual unitaries that act on each of these acts on a single qubit, for some coefficients that you can determine from the spectrum of the generator. So that's very nice. It's very efficiently implementable in a quantum circuit. There are additional steps that I'm not talking about here, having to do with how you prepare the initial quantum state and how you measure it at the end to get out the forecast that you really want. Again, I don't have time to talk about this here, but I'm happy to talk offline. But the point is that there is an algorithm that is, on the one hand, consistent as the number of qubits increases. It has this positivity preservation property that I mentioned earlier, and it has a quantum advantage in this very specific sense. I don't want to kind of like overinterpret this or oversell it. It basically has the property of simulating a space which is exponentially large in the number of qubits of classical observables using a polynomial number of quantum resources, so circuits that have order n square quantum gates. So a running time that grows as the square of n to simulate an exponentially large space of observables. These are some examples with very basic systems. So these are embarrassingly simple systems you could write in one line of MATLAB to, like a harmonic oscillator where we want to just predict the evolution of sine x under just a harmonic oscillator. But the point here is to demonstrate that an ensemble of quantum measurements, these are simulated quantum measurements, track the true evolution reasonably well. Here, D is the dimension of the system, and N is the number of qubits used in these simulated experiments. Also in higher dimensional tori, where we have quasi-periodic dynamics, it basically works as expected, at least in these simulated examples. But we also did an actual quantum computation done over with my collaborators in Germany on an IBM quantum processor. We were only able to scale this up to 3 qubits before noise basically made this kind of like render garbage in some sense. But at least for the qubits that we were able to scale it, the ideal and simulated versus actual quantum experiments are in good agreement, and we get somewhat decent results for this one-dimensional harmonic oscillator. This theoretically should become better if we are able to increase the number of qubits without being affected by noise. Okay, so I think I have about 7 minutes. So by my talk. So now in this last part, this is more like a work in progress. So I talked about these example of pure point spectrum systems. These are highly structured systems that are not arguably the most typical, even though there are wide classes of dynamical systems that can be transformed into this into that form. Now we want to move towards generalize this to more to classes of potentially mixing dynamical systems, and for that there are basically two main challenges one has to address. So a mixing dynamical system will typically, well, not typically, it's actually an if and only if condition, will be accompanied by a non-trivial continuous spectrum of the Koopman operator on L2. So if we were to design an algorithm that is based on this eigen decomposition of the Koopman operator, we have to find a way of discretizing the spectrum, essentially consistently approximating it by a discrete spectrum system. But then on top of that, we need to be able to translate then that discrete spectrum system into a quantum algorithm. So we're not there yet in full generality, but we are making some progress I will be talking about now. And this is in collaboration with Mohammed and Michael, who are postdocs at Dartmouth, and Claire, who is a PhD student at NYU. Okay. So let's, well, just to show up, put these formulas back up here, that if we have a measure-preserving flow on I'm calling it phi t, we can consider the Koopman operator on L2. Now we're back into L2 space for now. As the composition operator, it is a unitary operator, and it has an associated infinitesimal generator under appropriate assumptions. And this operator is typically unbounded and it has continuous spectrum. So we want, in our work, we've developed techniques that take this generator and using some smoothing techniques by kernel operators, approximated by a family of operators, v tau. Tau here is some approximation parameters that have the property that they are skew adjoint, and they are either compact or they have compact resolvent. We've had like two different techniques, this being the more recent one. And by that, if you have a compact operator or an operator with compact resolvent, means that they're diagonalizable. They have an orthonormal basis of eigenfunctions. You can think of as approximate Koopman eigenfunctions that also work for potentially mixing system. And as tau goes to 0, these schemes are set up such that the approximate generator converges in a spectral sense to the original generator. So I'll show you first a couple of examples of how this spectral approximation technique works in practice. So the first is just a sort of a sanity check. If we take an ergodic torus rotation, so this is in 2 dimensions, and we compute eigenfunctions of this approximated generator, we should basically recover the Fourier functions, which are the true eigenfunctions. And this works to high accuracy. These are plots of the real parts of the eigenfunctions on the torus, a 2-dimensional periodic box. Here we have the real and imaginary parts of the eigenfunctions that should land on a circle when they are of unit radius, when they're normalized, and the real parts sampled along dynamical trajectories, which should be pure sinusoids. So this checks out, but we can also apply this method to chaotic systems like Lorentz 63, which is one example. One of the few examples that we have, there's a rigorous theory that is actually mixing. So the Koopman operator does not have any non-trivial eigenfunctions in L2, meaning non-constant eigenfunctions in L2. So in this case, we produce these observables, which are not true eigenfunctions. They are approximate eigenfunctions in a genuine sense. They're not approximations of eigenfunctions, but they exhibit some of the qualitative properties of eigenfunctions. They are observables that have an approximately periodic evolution under this chaotic dynamic. So these actually have a decorrelation time that is several multiple times of the Lyapunov time scale of the system. You can see them here as the real plots plotted on the Lorentz attractor. So there's an entire spectrum of this eigenfunction. I'm just showing here a few examples. So we have this methodology, we can produce discretizations of the spectrum for these systems. Now we would like to implement it in the context of a quantum algorithm. So here I'm going to loop back into these Hilbert spaces, these reproducing kernel Hilbert spaces that have the properties of being closed under multiplication in a suitable sense. Now I'm giving a more precise definition. We're calling these spaces RKHS for reproducing kernel Hilbert algebras. The idea here is that if you have a Hilbert space, H, and there is an operator that reproducing kernel Hilbert space, and there is a bounded operator that maps the Hilbert space into the tensor product with itself, you can think of this, and this operator is bounded, so it has in particular this formula applied to the kernel, then you can think of this as a dual to multiplication. So multiplication as an operator in a Hilbert space, it takes two functions, so an element of the tensor product of the space with itself, and it produces a new function which is given by the product of the two functions. So this operator is like a co-multiplication. It's like a dual of the multiplication that takes one element and produces an element in the tensor product. And so the adjoint in this case is going to be the actual pointwise multiplication operator. So we have these two important operators that allow us to go from H to essentially to its tensor powers. There is some coassociativity structure for this operator that allows you to extend this to arbitrary tensor powers. And here we can go down from the tensor product to the space itself. Okay. And we want, why do we care about this here? Well, first of all, these spaces have combined several useful properties from spaces of observables. So I'm just listing them here in comparison with other spaces of functions. But for us, we want to exploit sort of like algebraic properties that come from the tensor product for these quantum algorithms. And in particular, we're going to be working with the so-called Fock spaces, which are generated by this RKHA. So what is the Fock space? Well, we take the tensor algebra of the Hilbert space, which is basically, you take the Hilbert space, direct sum with a tensor power with itself, and all the other tensor powers, and also the complex numbers, so like the zeroth rank tensor in some sense, and it's closed under an appropriate inner product, and that forms a so-called Fock space. This is also a Hilbert space that is used, you can think of it as a space that describes a many-body quantum system. If you have a quantum state that consists of n particles, it would be an element of the nth tensor power of the Hilbert space in this infinite direct sum. So this is used very heavily in areas like quantum field theories or solid state, condensed matter physics, and so forth. And so we're building a Fock space out of our Hilbert space, and we can take our approximated generator, this v tau, and lift it in some sense into an operator that acts now on the Fock space. So why do we do that? Well, the reason is that this operator we build it such that it has discrete spectrum, right? But not all discrete spectra are equal. In some sense, in the pure point spectrum case that I was talking about earlier, this torus rotation, the spectrum was highly structured. It had the structure of an additive group. Whereas if you discretize a continuous spectrum, you will get a discrete spectrum, but it's not necessarily a group anymore, right? So what we're doing here is we are dilating, if you wish, or lifting the generator into a space where we're going to force, by hand in some sense, the spectrum to have a lattice structure, basically because the generator satisfies this rule, which is like a Leibniz rule with respect to the tensor product. And in particular, the unitary evolution that's being generated is multiplicative with respect to the tensor product. Similar to what we had in the case of a torus rotation, but now we're doing this more abstractly on this Fock space. And so I'm going to go through this very quickly. I'll promise I'll finish in a minute. We can basically create versions of these these quantum schemes that I showed earlier, but now operating on the Fock space. And how do these schemes work? Well, you take a unit vector in your RKHS, which is like the quantum state vector that I was showing earlier, like a square root of a probability density. And you can actually distribute it into the Fock space by computing its nth roots. So think of take a Gaussian function, compute its nth root. It's going to be again a Gaussian function that has higher variance. It's going to be like a coarser distribution. And we're going to, in some sense, coarsen our distributions, but then take tensor products of these coarsened distributions, evaluate and embed this in the Fock space. We can advance dynamically each of the factors of this tensor product, and then compute a quantum state expectation at the end to produce an approximation or like a forecast. And it turns out this whole procedure can be implemented as so-called a tensor network, which is basically each node here corresponds to an array of numbers that you can more or less use to evaluate this computation. It has the structure of a tree, and I can talk about this more later on. We apply this to one a dynamical system which is on the torus, which has the properties that it's not, it doesn't have any continuous Koopman eigenfunctions. It has these more interesting approximate eigenfunctions. And just as a final slide here, comparing the evolution of a Gaussian distribution on the torus. This is the true dynamics over time under the system that it exhibits all this stretching and basically complicated dynamical behavior with, this is like an EDMD type approximation where you can see, for instance, failure of positivity preservation and also a lot of noise because basically we're trying to approximate a function in this basis of approximate eigenfunctions which are not smooth for the system versus the version here in the Fock space, which is positivity preserving, but also has basically a good forecast skill compared to the classical method. So I will end up here with this important slide, and thank you very much for your attention.
Thank you very much. We have time only for a quick question, if there is one. No, so we can discuss with the speaker during the lunch. Thank you very much. Next speaker is Javier Jimenez Lopez from the University of Alcalá. Javier.
Thank you. Good afternoon, everyone. I'm Javier Jimenez, a physics student from the University of Alcalá, and I'm here to present the conference named Quantifying Chaos in the Double Pendulum with Lagrangian Descriptors, which is a joint work with the Professor Victor José García Garrido from the Physics Department of this university. So the conference will go as follows. First, I will talk about our motivation, our main goals from the beginning. Then I will explain why the double pendulum, and a little bit about Lagrangian descriptors again, and the case indicators we have used, which are more or less the same that Professor Skokos presented this morning. And then I will talk about our main results and summarize a little bit them in the conclusions. So first, the main goals were to do a parametric study of the double pendulum, but using Lagrangian descriptors because of their well-known advantages, and to develop new methods to analyze dynamical systems in general. But one can ask the question of why the double pendulum. Well, it's a very easy, it's a very well-known system, and it's very simple, but it has a lot of different dynamical behaviors that are interesting to study. And it also has, it also shares fundamental characteristics with other dynamical systems, such as those in celestial mechanics, like the one that were shown in the paper cited there. And if someone is further interested in our work, you can find it in this paper, which is the one we've done. So here we have a little diagram of the double pendulum, very easy. Double pendulum is just another pendulum with another one attached to it. And we have defined these non-dimensional parameters, which are the ratio of length, called alpha, and the ratio of mass is called sigma. And all our study will be based on these two parameters. So after obtaining the Lagrangian using a classical procedure, we can obtain the Hamiltonian, which introducing the matrix b to the -1 can be written using matrix notation. And the parameters we have previously defined, where we have the angle vector, the momentum vector, and the angle difference, which will be interesting to introduce. And well, notice that the Hamiltonian is clearly divided into terms, but I would like you to focus on the main thing, which is that the kinetic term is not diagonal, which will be important in the analysis we will do later. And obviously, after having the Hamiltonian, we can compute the Hamilton's equations, and introducing again another matrix, this time the C matrix. We can write them down in a compact way using matrix notation and the parameters we have previously defined. Now I will focus on the potential energy for a bit. As we can see, it's depending on both parameters and also only on the angular coordinates. And it has 4 critical points, one minimum, 2 index 1 saddles, and an index 2 saddle, whose energies are given in terms of the non-dimensional parameters we have already defined. And notice that depending on the values of the parameters, one of these two relationships will be followed. And the physical interpretation of this relationship is that depending on the values of the parameters, the heights of the index 1 saddles will be swapped when we see the potential energy surface as a 3-dimensional plot. And here we have a contour plot of this potential energy surface for one of the special cases for this system, which is when both masses and lengths are equal. And I will ask you to remember this case because it's a very interesting one we will discuss later on. Some people have already talked about them, but here we have our Poincare section, which I will just talk about the peculiarities of our Poincare section, which are we selected to fix the second angle to 0, which physically means that the second pendulum is hanging downward. And then we will select points in the P1 theta 1 plane and calculate the values of P2 once the energy of the system is fixed. The picture shows the Poincare section for an energy of 20, and again the special case I was talking about, and we can clearly see we have regular and chaotic dynamics almost always. But I want you to focus on the extra condition we have there when we define the Poincare section, because this arises from the fact that the kinetic energy is not diagonal. And this is because we have a second order polynomial equation to calculate the second momentum we get when we go to the Hamiltonian I have previously talked about and get this equation. As we can see, the coefficients depend on the parameters we have already talked about, but we have a problem because this equation will yield 2 solutions. So we have to select the one which is correct because the Poincare sections need to be uniquely defined. So in order to do that, we defined the quantity delta, which is the square root of the discriminant of this equation, and we will select the second momentum so that this quantity is bigger than 0, and this will ensure that the Poincare section is uniquely defined. So now a little bit about Lagrangian descriptors again, but I will be fast. So Lagrangian descriptor, we will obtain it from a dynamical system written as a set of ODEs, where we have introduced the f function, which is the function we have defined here as a non-negative function that depends only on the initial condition. We have used the definition with the p-norm from functional analysis, and as you already know, the forward descriptor will unveil the stable manifold, and the backward descriptor will unveil the unstable manifold. And in order to quantify the chaos, which is what we were trying to do, we have used chaos indicators derived from the Lagrangian descriptor because of those reasons. They are very easy to calculate. We just have to add an extra differential equation to our system, and the computational time is reduced considerably. And yeah, it's a little bit more than 90% in the success rate. It's not 100% as Solid provides, but as we wanted to do a parametric study which involves a lot of computation, we prefer to have some misclassifications rather than being 100% accurate and provide more results. So these are the chaos indicators. 3 of them were presented by Professor Skokos this morning, the first 2 and the last one, but my Professor Victor proposed the 3rd one, which is also quite interesting, as we can draw an analogy between this indicator and the discrete version of a gradient, as well as we can do something similar with the S indicator and the discrete version of a Laplacian, which was also commented this morning as an approximation of the second derivative. But what these functions do is to compare the value of the descriptor for the main trajectory with the value of the descriptor for the neighboring trajectories, whose initial conditions are the y sub I, where the I sub I is the 8th canonical basis vector of Rn, and sigma sub I is the distance we select to the neighbor. In our paper, we decided it to be 10 to the minus 4, as it has been shown to be a good distance and provide good results. Also, please note that we are only using the forward component of the descriptor, as it has been proven that the chaotic behavior can be visualized using both parts, so it will reduce the computation time. After having the mathematical framework we will use, we have to select the simulation time for our system. And selecting a regular and a chaotic initial condition, the regular is the blue one and the chaotic is the orange one, we did a time evolution study of the 4 indicators, and we selected the time of simulation to be 700 units of time. As we can clearly see, there is a separation between the values for regular and chaotic initial conditions. Notice that from this point on, we will only use the S indicator, as it seems to provide the best results, and it behaves very well with the algorithms we have developed, in specific with this one. So we have simulated 10 to the 4 random initial conditions for each energy value, and we have classified them with an algorithm Victor and I developed in order to obtain the value of the threshold. Professor Skokos has already talked about it this morning. So what we did was to then plot the classified initial conditions above the Poincare section, and we can see that only by classifying initial conditions we can reconstruct the Poincare section of the system. Notice that, yeah, there are some misclassifications, as the point we can see in red there, but there are very few of them, so it's not relevant at all for our analysis. As it's a parametric study, we had to select the value of the parameters we were going to use, and we decided to use powers of 2. So we could use logarithms to do all our plots linear. And as energy values, we selected 40 energy values equally spaced between the energy of the minimum and the energy of the index to saddle, and 130 energy values above the energy of the index to saddle with unit step. So the first result we have is the maximum chaotic fraction of the system as a function of the parameters. What we can see in this plot is that if we fix sigma, the system becomes more regular as alpha goes away from unity. And if we select alpha to be bigger than 1, the system behaves better when we are getting sigma bigger, and if alpha is less than 1, the system behaves better when sigma is getting larger. So this is what this surface represents, but it's more interesting to look at the projection in the parameter space, as we can see some kind of symmetries with respect to both parameters, and in specific to the point where both masses and both lengths are equal, which is the special case I was talking about before. After we plot the chaotic fraction curve as a function of energy, and we observed some sudden peaks and valleys, which when we did the Poincare sections for these 3 but close energies, we saw that the phase space has a very different appearance even though they are very close energy values. So this might be related to bifurcations and the destruction and creation of CAM structures in phase space, and it's quite interesting because usually you will expect chaos to be reduced when you increase energy and don't have any type of fluctuations. And our last contribution was to show that this chaotic fraction curve has some exponential trends, both at the very beginning, as we can see here, and I will show later that also for high energies. So for the very beginning, we use an exponential model where you can see all our coefficients and the R-square parameter value, which is indicating that we are in the right track with this type of fit. And also notice that the chaos grows very fast from the beginning of the curve. And here we have also for the decreasing chaotic section, where we also tried a linear fit, but we quickly get rid of that idea because of its poor performance. Also notice the good R-square parameter values, so again it's a good fit for this section of the curve. And in this graph we can see them both combined, and maybe you can appreciate more that the trend is clearly exponential in both cases. Also, something we should remark is that when forcing an exponential fit in the high energy section, we are forcing the system to behave completely regularly when energy tends to infinity. Even though this is an assumption we did and the curve points in that direction, there are systems for which this assumption is clearly incorrect. So let's sum up. The maximum chaotic fraction is dependent on the mass and length ratios, with the maximum being achieved when both parameters are equal to 1. The chaotic fraction is energy dependent and has exponential tendencies, both at the very beginning and at the very end for high energies. And we have seen sudden peaks and valleys in the chaotic fraction of phase space that might be indicating that some structural changes are taking place in phase space due to Tori and the appearance of bifurcations. As future research, we believe that developing control strategies for handling the chaotic behavior of the double pendulum or analyzing the chaos fraction curve for other systems, as well as studying the CAM structures, will be great topics to continue researching about. Thank you for your time.
Thank you, Javier. We'll postpone the questions for the lunch. So thank you, Javier. And the next speaker is Dylan. You can use this. Can I use that? Yes. So next speaker is Dylan Terón. Can put in the okay.
Can you hear me? No.
Is
it not on?
Yeah. Yes.
Oh, there we go. Fantastic. I will get right. There we go. Okay. And is it this one?
You can look at the. You can yes. To go to the
Short speech.
the rest.
There we go.
Yes.
No. Yes. There we go. Okay. So, good day everyone. My name is Dylan Terón, and I'd like to begin by thanking the organizers for putting this incredible conference together. And I'd also like to take time to wish Professor Wiggins a happy belated birthday. So my presentation today will be on revealing the phase space structure of dynamical systems described by fractional differential equations, in particular with application to the Duffing oscillator. This work was done in collaboration with Hadi Sasanto, one of the organizers, Makrina Galu, and my supervisor, once again from Cape Town, Harris Skokos. And I conducted this research while undertaking my master's studies at the University of Cape Town in the Nonlinear Dynamics and Chaos group. The outline of today's presentation, or my presentation, will involve a brief introduction where we will touch on why we conducted this research. We will then touch on some of the widely implemented definitions of fractional derivatives before touching on some relevant integration techniques. And then, because I'm sure at this point we're all sick of Lagrangian descriptors, I'll just brush past that. But nonetheless, we will apply the Aldi's method to the Duffing oscillator governed by FDEs to reveal the underlying phase space structures. So firstly, what is fractional calculus? Well, very basically, fractional calculus is a branch of applied analysis, and it's extending the concepts of integration and differentiation to non-integer orders. And at the same time, since the 1970s, fractional calculus has found more applications in a wide array of the applied sciences, such as hydrodynamics, electrodynamics, quantum mechanics, and so on. So despite it being an extension of topics that we're all extremely comfortable with, and its increase in utility, providing a physical or geometrical interpretation of fractional integration or differentiation has proven quite difficult. Nonetheless, there have been multiple attempts to offer explanations, for example, linking fractal geometry with fractional calculus, or measuring the path and acceleration of a point in motion of a system described by FTEs, and trying to offer a geometric interpretation accordingly. In our research, we offered a way of qualitatively presenting the phase-space structures associated with systems described by FTEs. So we only look at a subsection of fractional calculus and not at fractional calculus at large. So firstly, I'd like to say that fractional derivatives, there are ample definitions, and these three that I have up on the screen are far from all of them. Another thing I'd like to note and emphasize is that fractional derivatives are non-local in nature. So they differ according to the time interval that the derivative is taken on. So the first derivative that we'll look at is the Riemann-Liouville, the RL fractional derivative, with its definition, I don't know, is this, there, being given over there. So the superscript RL preceding the differential operator just indicates which definition we're referring to. The subscript A plus over there tells us that this derivative is just taken from a real value A to a point later in time t. Next, we have the superscript alpha, which is just the fractional order of the derivative, and it's an element of all positive real numbers, including 0 and excluding natural numbers. And on the right-hand side of the equation, in that first fraction, the denominator is just the usual gamma function of n less alpha, where n is just the floor function of alpha plus 1. Our second definition is the Grindelwald-Letnikov GL derivative, and it is equal to the RL derivative. The reason why I showcase it here and why it's important for our particular study is because it's a discretized definition. So it's very useful when trying to implement this, the RL derivative numerically, because instead of letting h over there tend to 0, you can set it as a very small number, so 10 to the power of negative 3, for example, and then it approximates the RL derivative. And lastly, we have the Caputo derivative, and the Caputo derivative is not equal to the RL derivative. Instead, the difference between the RL and the Caputo derivative has explicitly been given here. The reason why I show this proposition is, once again, to demonstrate that we can rewrite the Caputo derivative in terms of the GL method, which allows us to discretize the definition and implement it with ease numerically. So now we have the RL and the Caputo derivatives, which are two definitions. And the reason why we want two definitions is to show that our method, or applying the LD's method to fractional derivatives, is useful to a wide class of definitions of fractional derivatives. Furthermore, in this study, we just use the simplistic case where alpha is just set between 0 and 1. Now, some relevant integration techniques. I'll just touch on this very quickly. The first integration technique which we looked at is a time reversible integration technique. This means that a unique solution exists. What I mean by that is you start with an initial condition, integrate an orbit forward in time. If you use that final point and integrate backwards for the same amount of time, you'll be left with one single unique trajectory. The second integration technique is a time irreversible method, and that means that a unique solution does not apply. So if you integrate an orbit forward in time and use the final condition and integrate backwards in time, you'll have two separate trajectories. Once again, the reason why we look at two integration techniques is just to showcase that this method is applicable to a variety of different techniques in the field of fractional dynamical systems. Lagrangian descriptors, as I said earlier, I'm just going to brush over that. The important thing is, just to reiterate, tau is the integration time. And for a system described by ordinary differential equations, ODEs, it does not matter how long we integrate for, in terms of for a simple system. Once the underlying manifolds have been revealed, in completion, if we integrate for longer, it won't produce any further subscriptions. So now that we have these different definitions, which model will we apply to? In particular, we chose the unforced and undamped Duffing oscillator. So a very simple system, but we chose this system because it's previously been used in Professor Wiggins and Macrina's book that I've now learned he wrote in 2 days. It's been applied over there to the system of ODEs and also to the system of stochastic differential equations at different points in a different paper. We set beta equal to -1 and psi equal to 1, which allows us to write the equations of motion very simply over there as a system of ODEs. And transforming this into a system of FDEs, we just rewrote the equations of motion in terms of alpha so that we can easily adjust that. So just as having a base case, this is applying the Aldi's method to the system of ordinary differential equations for 3 different integration times, tau equals 5, or as this figure over here, 10 and 20 respectively. As we would expect, the underlying phase space structures do not change. What we do see is infinity symbol looking shapes, and we see the fixed points at along the y equals 0 axis and at x equal -1 and x equals 1 in all 3 panels. Now moving on to the system described by fractional differential equations. As I said earlier, we wanted to make sure that applying the Aldi's method to a system described by FDEs is relevant to a broad class of such definitions. So what we did in the first column is we used the definition, the Riemann-Liouville definition of a derivative, along with the time reversible integration system. And then for the next 3 columns, we used the Caputo derivative along with the time irreversible integration scheme. The reason that the Riemann-Liouville, so this first column of plots, only has an integration time of tau equals to 5 is because for the backwards integration of fractional derivatives using the time reversible method, it requires ample computational limits. So therefore, we were pretty much restricted to this one integration time, and that's why we produced it over here. So looking quickly at the system with alpha approximately equal to 1, the first row of results, alpha equals to 0.49, we see that once again we have this infinity-shaped structure, and regardless of what definition we used for the FDEs or integration technique, the underlying phase space structures acted as if they were normally hyperbolic invariant manifold, or approximated that at the very least. They are not, as we know, they are non-local in nature. However, the moment we decrease the fractional order to 0.98, seen by the second row, we see that this no longer holds true. So if we first look at the results for the time irreversible integration system, so these 3 panels over here, for tau equals 5, this figure over here, we once again see similar results to the row before and to the system of ordinary differential equations. But as the value of tau increases, we have additional structures outside of the infinity-shaped structure, demonstrating very clearly the non-local nature of the FDEs. That being said, we do see symmetry about the x equals 0 and y equals 0 axis, which is not seen in the result relating to the Riemann-Liouville derivative. Here we see point symmetry, and the reason we see point symmetry is because there's breaking of the infinity-shaped curve at those points over there. But nonetheless, at this point, the LDs were revealing the underlying phase space structures. Reducing the value of alpha further to 0.95, we see once again that there are additional structures outside of the infinity-shaped curve, and for tau equals 20, over the specific interval that we have chosen to examine our results, you can't quite see it. However, if you do extend this interval, you will be able to see that the structures have pushed out a little bit further. And for the Riemann-Liouville definition of our FDEs, we see that the separation of the underlying phase space structures has increased. And for the first time, we see the introduction of initial conditions that have been colored white. Why do we have these points? Well, for the same reason that I was stating, that we were only able to use this integration time for tau equals 5, we ran into some computational limitations as we started to reduce alpha, the value of alpha, which purely applies only to the integration scheme that we have implemented. And we can see that this is increased as the value of alpha is decreased in this last plot, just showcasing that this integration technique is reaching its limitations. So now that we've seen we are able to reveal the underlying phase space structures, how is this useful? What does this tell us? So basically, as I'm sure we all know, LDs have been used to study the phase space transport of dynamical systems previously for systems described by ODEs or stochastic differential equations and so on. And we decided to have a look and see if that applied for fractional differential equations. So what we did is we selected the system with alpha equals 0.95, and we chose the two different definitions of fractional derivatives, so the Riemann-Liouville and Caputo. Furthermore, we separated the structures into the LDs method, the forward Lagrangian descriptors method and the backwards Lagrangian descriptors method, which is shown over here. So the two panels on the left are related to the Riemann-Liouville derivative, and the last two are related to the Caputo derivative. Then what we did is we selected three initial conditions shown as blue dots. We then integrated these initial conditions forwards and backwards in time. And we can clearly see here that, once again, as seen for ordinary differential case and the system described by SDEs, that the underlying phase space structures do indeed govern the phase space transport. We can see that the forward integration of orbits, despite the definition that we use, they're approximately equivalent. However, the real difference comes in when we look at our backwards integration case, where the symmetry or the equivalence is no longer seen. But nonetheless, we do still clearly see that the underlying phase space structures do govern the phase space transport of the system. So wrapping up, we applied the LDs method to a system governed by FDEs, the Duffing oscillator in particular. We revealed the system's underlying geometric features and demonstrated the influence of the different fractional orders. So going back to the very first slide, we were able to show that by implementing the LDs method, we can compare different alpha values on a system and geometrically interpret the underlying phase space structures, which is important. And at the same time, we showed that the LDs method can be applied to systems by FDEs in order to examine phase space transport, which is a new result. Thank you very much.
Okay, thank you very much, Dylan. And now it's time to go for lunch. Okay, thank you.
So please try to be here again at 3:45 for the evening session, okay? So we will go faster today because I will hand distributed menus when we are on the restaurant, so so that you can choose. And please keep the menu for tomorrow as well. You have the menu for today and tomorrow.
behind schedule. So it is a pleasure to introduce to you Holger Wolkens from Groningen, that he will speak about saddles in the charge 3 body problem.
Thank you. Okay, so let me start by
thanking the organizers for the kind invitation to speak at this very well organized and special conference, organized on a special occasion to which I will come in a moment. So what I will do in my talk is report on some work that I did with my colleague Igor Hofein from Groningen. Part of this work has already been published in 3 papers in Indagationes Mathematicae, but it's still actually work in progress. So yeah, before I start, let me also congratulate Steve on the occasion of his 65th birthday. And my understanding is that in a way you could even say that you already had 2 birthdays this year. So I wish you all the best for many, many years to come. And I'd like to also join in thanking you, because I really also benefited a lot from collaborating with you. So in fact, I spent 5 years with Steve in Bristol from 2002 to 2007. And my most successful papers are all from that time. Yes, so I think for nonlinearity, we are maybe even the record holder with, as far as the length of the paper is concerned, almost 120 pages. So let me briefly tell you what this work is about by illustrating in terms of the HCN CNH isomerization problem. So we look at a triatomic molecule that we look at for vanishing angular momentum. Then it has 3 degrees of freedom, for which we choose the so-called Jacobi coordinates. So it's described by it as a Hamiltonian function. We look at it classically with a Hamiltonian of type kinetic plus potential, where the potential, well, is some complicated function that you can look up in the literature. To give you an idea of what the system dynamic is like, so here I show isopotential surfaces that indicate that there are 2 minima of the potential that correspond to the hydrogen being either on the nitrogen side or on the carbon side. And then there are 2 saddles, symmetry related, and these saddles, they induce some kind of bottleneck in the phase space of the system. And the idea that originates from chemistry to compute the rate for going from one isomer to the other is to put or to define a surface, we call it a dividing surface, in this bottleneck region and compute the rate from the flux through this surface. Yeah. But for this to be useful, you need to have the following property. Namely, here we have I show 2 trajectories that start very close by, one making it to the other side and the other one doesn't. And what you want is that the trajectory that makes it to the other side intersects the surface exactly once, and the other one should not intersect it at all. So how can you do that? So more specifically, what we will do is, this is a Hamiltonian system, not depending on time, so energy is conserved. What we do is we will fix an energy above the saddle. And then on this energy surface, so the energy surface, we have 3 degrees of freedom, phase space is 6-dimensional, energy surface is 5-dimensional. We need to define a 4-dimensional surface. And this 4-dimensional surface, in order to divide it into 2 pieces. In order to define this 4-dimensional surface, it is useful to understand that, or to note that the energy surface locally has a structure of a cylinder. It's R cross across a 4-dimensional sphere, yeah? So, or interval across a 4-dimensional sphere if you intersect that with a suitable ball here. Okay, so in order to hence divide that into 2 pieces, you need to define some suitable 4-dimensional sphere. And well, the key insight is that you define this 4-dimensional sphere in such a way that its equator is formed by a 3-dimensional sphere, where the 3-dimensional sphere is a normally hyperbolic invariant manifold that can be shown to exist near such saddles. So more specifically, the saddle is a saddle center-center equilibrium point in this Hamiltonian system. Okay, so then this S3, this 3-sphere, divides this S4 into 2 hemispheres, which are intersected by the trajectories going from one isomer to the other, or the other way around for the other hemisphere. Okay, and this, so this dividing surface has the property that it transfers to the Hamiltonian flow, and it minimizes the flux. Moreover, this normally hyperbolic invariant manifold has stable and unstable manifolds, which are codimension 1 in the energy surface. So that's also how you can distinguish between the fates of these two trajectories, because they are lying on different sides of this stable or stable and unstable invariant manifolds. Okay, so this has its origin of conception in chemistry, but it has many, many applications in atomic physics or, well, condensed matter physics, certainly also celestial mechanics, and there are really many, 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 many applications. So when I was in Bristol, we somehow were obsessed with saddles. I really saw saddles everywhere, or I started to see saddles everywhere. I could not look at the weather forecast without looking for saddles. So you notice here one. Or even when I looked at my kitchen table or kitchen chair, my brain somehow started to see saddles. So the saddles I want to talk about a little bit is a little bit of this kind. So this is a picture some of you might have seen before. This is a effective, or these are the lines of an effective potential that correspond to two heavy bodies, like in this case the Earth and the Sun, that are co-rotating. And then you look at the potential that a third light body sees in a coordinate system that is co-rotating with the two bodies. Yeah? This is the so-called circular restricted three-body problem, and we look at the gravitational case. Yeah? So the interaction is via gravitation. And, well, there you see, notice 3 saddles, 1, 2, 3. And there are also other equilibrium points, this one and this one. These ones are actually named after Euler, and these ones after Lagrange. So Euler and Lagrange do not only show up for naming descriptors, but also in this setting. So this one, this equilibrium point is, for example, used where the current James Webb telescope is placed. Yeah? Okay, so and for these saddles, again, you could discuss transport, for example, from the neighborhood of the Earth to the neighborhood of the Sun. Yeah? Okay, but it's already important to note that these equilibria here, they actually, well, are in some sense relative equilibria, because what you started off with is a co-rotating two-body problem. Yeah, so you start off with a, and then you look at the forces on a third light body that does not affect the co-rotating pair. So you start actually off with a time-dependent system, right? But this time-dependent system is special in the sense that it's periodic. So what you do is actually, in order to get this to this picture, is you reduce this periodicity. So you reduce an S1 symmetry. Yeah. Okay, and in that sense, these equilibria actually can be looked at as relative equilibria. Yeah. Okay, so that because relative equilibria is what we want to talk about in the rest of the talk. So let me first tell you what I mean by an n-body system. So an n-body system is just a collection of n points in R3, where you might want to take out the so-called collision set. That is a set where the particles, at least 2 particles, sit on top of each other. And then it's just described by a Hamiltonian, which is of type kinetic plus potential. And we want this potential, and hence the full Hamiltonian, to be invariant under the Euclidean group SE3. So under translations and rotations. Yeah. Okay, and for the special case where the potential is of this form, we call that the charged n-body problem. Yeah, so the charged n-body problem, it's just that these coefficients are arbitrary. If they are products of masses, we have the gravitational case. Maybe you need to, yeah, the gravitational case. And if it's a product of charges, then you would have a Coulomb interaction. Yeah? All this is covered under this more general type of potential. Okay, so when you deal with relative equilibria, at least in celestial mechanics, you will inevitably encounter the notion of a central configuration. So when you have ever been to a celestial mechanics conference, they always talk about central configurations. Confused me very much at the beginning. Okay, so what is this? Well, that's a notion in configuration space, huh? Not phase space. So at first, notice. And what is this? So it's a configuration where all the forces are proportional to the difference vector of the so the force on the i's body is proportional to the difference vector to the common center of mass times the mass of the ice body, and then you have a common proportionality factor, lambda. And this lambda is then called the multiplier of the central configuration. Okay? And that will be important for reasons that you will see, I hope. So in particular, these central configurations lead to special solutions of an n-body system. So namely so-called homographic solutions. What is a homographic solution? A homographic solution is a solution of this form where you start with some initial condition and you choose it to be a central configuration. And then the motion consists of rotations, so you have a time-dependent rotation matrix here, times a dilation, times a scalar, f of t. Yeah? So that is a very particular type of motion. In general, that doesn't exist for any initial condition, but if you take as the initial condition a central configuration, then this is a solution of the equations of motion. Okay. Yeah, so these central configurations have actually already been found by Euler, respectively Lagrange, or these homographic solutions. So here is a case where the three particles are on a line. When you look at the corresponding homographic solution, each of these particles traverses an ellipse individually, but at each moment in time, all the three particles sit on a line. Yeah? And likewise here, so you start with an equilateral triangle, that's a Lagrange homographic solution, and each of these trajectories or solutions of each body follows again an ellipse individually, but together they always form an equilateral triangle. Let me illustrate that in terms of some animations that you can find on Scholarpedia. So there's a Scholarpedia page for central configurations. These animations are done by Rick Merkel. So this is what you get when you start with an equilateral triangle. You start with some special velocities. So each of these particles or bodies traverses an ellipse. So at the same time rotating and changing the distance in such a way that it stays on an ellipse, and at each instant of time it forms an equilateral triangle. So you could also release the particles with zero velocity, like it's done here in the central configuration, and then they collide at the same time at the origin, at the center of mass. Yeah? Moreover, you could choose the initial velocities in such a way, in a special way, such that the size of the triangle doesn't change at all. Yeah? So then you get special ellipses which are circles, and this is in fact a relative equilibrium. Yeah? Okay. Now, let's look at relative equilibria a little bit more systematically. So, in order to do that, we look at a map that from the phase space to the constants of motion for an n-body system. Because of rotational symmetry, we have that angular momentum is conserved. Because of translational symmetry, we have that the total momentum and the center of mass is conserved, if you choose that to be zero. Yeah? So this map is then a map from, and of course, in addition, the Hamiltonian is conserved because it's not time dependent. This is called then the integral map. It takes values in R10. Okay, now what you can look at is the critical points of this map. So when does the derivative not have full rank, at which points? And there are three possibilities. Either the qi and pi of all particles point in the same direction. Yeah, that's one possibility. The other possibility is that actually q and p form an equilibrium point. Yeah, correspond to an equilibrium point. The third is that it is a relative equilibrium with respect to rotation, like the rigid rotation that we had in the animation. Okay, now what about these different cases? Well, first, equilibrium points. So, for example, for a gravitational n-body problem, there are no equilibrium points. You can easily see that. There is the only proof in my talk by applying Euler's homogeneous function theory, right? So the potential is homogeneous of degree 1, minus 1. So you have this equality. So if there would be an equilibrium point, then all these would vanish, all these factors, right? The forces would vanish. So this would need to be 0, but for a gravitational potential, this is strictly negative, right? So that is not possible. In the general case of a charged n-body problem, this does not exclude the existence of equilibria, right? But it at least says that if you have an equilibrium, it must have zero potential. Yeah? Okay, so in a way, the equilibria are not so interesting. Also, these points are not so interesting because they really correspond to not only collinear configurations, but really to collinear motion, right? It's not only that the q's are along one line, but also the p's are along one line. Yeah? So, for example, if you are choosing an integral surface where the angular momentum is different from zero, such points are not contained in the integral manifold. Yeah? Okay, so hence we look at relative equilibria. Okay, so in order to understand the result that I will show in a moment, you need to note that when you look at the forces, the force on the ice particle is that you can write that as a linear combination of the position vectors. Yeah, I mean that is a trivial computation. Yeah, but the coefficients here we call them alpha ij. So they will form a matrix that we will look at in a moment. Okay, now central configurations. If you have a central configuration that is planar, a planar central configuration, yeah, with a positive multiplier, then this can give you a relative, or this, yeah, can give you a relative equilibrium. Namely, so if there is a vector E in R3, which is perpendicular to this plane, so all the particles are contained in the plane perpendicular to this E, then you have the condition for a central configuration. And if you choose the momenta in this way, yeah, so all perpendicular to the position vectors for every particle and contained in the plane perpendicular to E, then this will give you relative equilibrium. Okay, so conversely, if you have a relative equilibrium that projects onto a central configuration, then the central configuration must be planar and have a positive multiplier. Yeah? Okay, so these central configurations, when they are planar and have a positive multiplier, they can give you relative equilibria. But in general, they do not give you all relative equilibria. Yeah? So in fact, yeah, this is just summarizing what I just said. So if you have a relative equilibrium that projects onto a central configuration, that must be planar and have a positive multiplier. And conversely, the planar ones with a positive multiplier give you central configurations. So the question is whether all relative equilibria are obtained from central configuration. So in order to answer that, well, this is a case when you are looking at the matrix A, which has these alpha ij that we just introduced as coefficients or as components. Then if the kernel of this A is one-dimensional, yeah, this is always contained in the kernel, but if it is spanned by only this vector, the kernel, then all relative equilibria are associated with planar central configurations. But if the kernel is bigger, then this is not necessarily the case. Yeah? Okay. So determining the kernel of A that is in general difficult. Yeah? So in fact, even the question of whether the number of central configurations is finite for 6 or more bodies is not known. Yeah? So the number of central configurations for the gravitational case, which is then the same as relative equilibrium, it is not known. And well, that's a famous problem. That's one of Smale's problems for the 21st century. Yeah? So if you want to have some challenging problem, that is one you could look at. But what we know is that if all these derivatives of the potential with respect to the mutual distances between the particles, if all these signs of these derivatives are equal, then every relative equilibrium projects onto a central configuration. And that is the case for the in the gravitational setting. Yeah? So in the gravitational setting, there's a one-to-one correspondence between relative equilibria, central configurations, hence the celestial mechanics people talk about central configurations all the time. Okay, so let's look at these central configuration a little bit more. So when you look at the equation defining a central configuration, it's easy to see that this is invariant under rotations and also translations. Yeah? So, well, That's very easy. But if in the case where this V here is actually coming from a charged three-body problem, then the V is homogeneous of degree -1, then it's even, this equation is even invariant under dilations. And what are dilations? This is just scalar multiplication of all the Q's with the same scalar. Yeah? That is a scaling invariance that you have there. Okay, so now let's focus on the case where we actually have three bodies. Yeah? And let's look at, well, let's more specifically write the potential this way. So we call the coefficients here now alpha 1 to alpha 3. Then you have the following result. If you are fixing the masses, yeah, if you are fixing the masses, and well, you can always change you can always scale in such a way that the third charge or the third coefficient is equal to 1. So this is not a restriction. Then there are 13 different regions in the alpha 1, alpha 2 parameter plane with a constant number of collinear central configurations. So 13 different. Yeah. So it's an indication that it's not such a trivial problem, right? So let's try to understand that. So a little bit. So in fact, for a given order of the bodies along the line, we are only talking about collinear ones. This number can be 0, 1, 2, or 3. That depends then on what the charges are. Yeah. Okay. So this is a picture. So this is the alpha 1, alpha 2 plane, and these lines alpha 1 respectively alpha 2, they are critical. And then in addition there is one other line because this line actually, if you would compactify this plane by including infinity, doing some stereographic projection or so, yeah, then this line, let's say it comes in, goes back over infinity through the pole, and then comes back somewhere here, and well, this way it goes all the way around, so there's only one curve. Yeah? In addition to the coordinate axis. So how can you understand that? Well, it's actually not difficult to see that if you reduce the collinear configurations, the set of collinear configurations by rotations, translations, and dilations that you get for n bodies, you get RPn minus 2, the real projective space n minus 2. So in particular, when you have n equal to 3, you get RP1, which is just a circle. Yeah? So a circle. Let's define a coordinate on this circle. Let's do that in this way. Let's call this coordinate u. And let's not look at the text, just at this. So u will be y divided by x, where y is the distance between particle 1 and 3, and x is the distance between particles 3 and 2. Yeah? And then, well, so we compactify the real line on which u lives by taking the union with infinity, and then, well, you get a circle, and then depending on where you are on this circle, or where u is with respect to -1 and 0, you have different orders of the bodies, namely the first body in the middle, the second body in the middle, or the third body in the middle. Yeah? Okay, so in fact, the collinear central configurations equation then actually gives you a polynomial equation of this form. So you have that they are given by u's that are zeros of this polynomial, which is of degree 5. Yeah? This is the famous quintic that Euler and Lagrange looked at for the gravitational case. Yeah? So in particular, if you would choose here products of masses, and well, that is what people looked at before. But in general, you will have this. Okay, and then, well, so then you get these 13 different regions in the parameter plane by looking at f of u equal to 0. That is the surface. And then, well, you have the discriminant, or the surface of vanishing discriminant, which is, if you intersect this with fu equal to 0 in this space here, then you get lines. And these lines, well, project to, in this case, when we look at the gravitational case, to the space of masses, and give some interesting structures, but they are all contained in the quadrant where one of the masses, at least one of the masses, is negative. So they are not interesting. Yeah? That's why in the gravitational case, there are always only these Euler collinear central configurations that have been known for hundreds of years. But in the gravitation, in the general case, well, if you project that to the alpha 1, alpha 2 plane, or scaled by alpha 3, which you can always set equal to 1, then you get these. If you look at that more closely, then you get these 13 different regions that I just showed. Yeah? Okay. So in fact, what you can show more specifically is that for a charged three-body problem, the number of collinear central configuration that must be one of these numbers: 1, 3, or 5. It cannot be anything else. Yeah. So that is also something we proved. Let's also look at non-collinear central configurations. So let me just show you the result. So when you have a charged three-body problem, then there is at most one non-collinear central configuration. Yeah. So a necessary condition is that all these alphas, the coefficients in the potential, that they have an equal sign. Yeah? But even that is not enough to guarantee you the existence of a central non-collinear central configuration, because you also still need to satisfy other equations, for example, the triangle inequality. And in particular, this shows that when you are really looking at a system that is interacting via Coulomb forces, yeah, so the alphas are really products of actual charges, then you have 0, 1, 2, or 3 collinear central configurations that give you relative equilibria, but there is no non-collinear one. It doesn't exist. Yeah? For a charged three-body problem interacting really via electrostatic forces, there is no non-collinear central configuration. I don't say that there is no non-collinear relative equilibrium. Yeah? That's a different thing. Yeah? Okay, so let's, because, well, that in fact it can happen. And let me show you an example. But for that, let's take a slightly different perspective. So what we do now is we are actually reducing our system with respect to the rotation and translations. And we do that in a symplectic way. So then, so the rotation group is three-dimensional. The translation group is also three-dimensional. So you can get rid of six many dimensions, right? At first. And so that is what is written down here. So it's a reduced Hamiltonian, or the Hamiltonian on the reduced space, reduced respect to the rotations and translations, so the SE3 symmetry. And that is then of this form. So you have 3n minus 6 many configuration variables. Then you have the conjugate momenta. They enter a kinetic energy this way. And you have a rotational term in the kinetic energy, where this J here is the angular momentum in a body frame. So this angular momentum is not the conserved one in phase space, but this is one as seen from a body frame. So that is not conserved anymore. So yeah, that's a little bit odd if you see that for the first time, that you start with a conserved angular momentum, then you reduce, you get then an angular momentum in a body frame that is not conserved anymore. So why is that a reduction? Yeah, that's a little odd if you see that for the first time. But the equations of motion, they are as follows. So you have they are canonical in these internal degrees of freedom, and then for the rotation, or for the J, you have this equation here that you might have seen from a rigid body before. Yeah. Okay. So yeah. So what is maybe also important to note here? So why is this written down this way? So, well, what you have is actually that the kinetic energy, which consists of a so-called rotational part and a vibrational part, yeah, so using chemistry terminology, that these two are actually coupled in various ways. Namely, what you have here is the moment of inertia tensor, or the inverse of that. That depends on the configuration, so it depends on these variables. And also the momenta are coupled to the j's via these magnetic terms. So they will, this coupling here, they will actually give you the Coriolis forces. Yeah? And the way this is written down is that this is in some sense coordinate independent. Yeah? So for whatever coordinates you choose here, you can compute the corresponding magnetic terms here, and you also have a so-called internal metric, and that will give you a Hamiltonian of this form. Yeah? It's always of this form. Okay, so from this equation, if you have some experience with rigid bodies, you might know that the angular momentum is, or the norm of the angular momentum is actually conserved. Yeah? The norm of the angular momentum is conserved, as it should be, right? I mean, it's a body angular momentum, but it's the former space-fixed angular momentum seen in the body frame, but the length doesn't change when you are moving, right? Okay, so hence the reduced phase space is the cotangent bundle over the space where these internal coordinates live times a sphere on which this j lives. Yeah? And if you count dimensions, let's say the n is equal to 3, and 3 many bodies, yeah, then you have 3n minus 6, that is 3. So you have 3 internal coordinates. And you have your j that lives on a sphere, two-dimensional sphere. So you have actually a phase space that is 8-dimensional. So the reduced space is 8-dimensional for a 3-body problem. Okay, so let's what we want to do is we want to look at that space. Well, not at the phase space, but what we want to do is we want to somehow describe the configuration of the system, or say something about the configuration of the system, and where the body angular momentum is pointing at. Because this information about where the body angular momentum is pointing at, that gives you some information about the orientation of your 3-body problem. Yeah, because it's always perpendicular to the, or it's described in terms of the plane, in terms of the co-rotating coordinate space. So if you know where the angular momentum is in that space, well, then you know how you are oriented in the original unreduced space. Yeah. Okay. So, and what we now do is, well, we don't look at the full configuration space, the full internal space, but what we do is we make use of the scaling symmetry, the dilation, and scale the configuration in such a way that this so-called moment of inertia is actually equal to 1. Yeah? So it means that in the 3-dimensional space, we just choose something 2-dimensional. Yeah? That's just a choice. And what we then look at is this dilation reduced internal space. That is what we call the shape space. Yeah? Because what we want to do, for example, is identify all triangles that just differ by scaling. Yeah? As an example. So instead of looking at a configuration, you look at the shape, and the shape should not depend on how big the configuration is in a way, right? Okay, so we have hence look at the space, which is the shape space, so the internal space with normalized configurations, if you like, cross a sphere on which the angular momentum lives. Yeah, so it actually, well, you can scale the angular momentum that it actually has length 1, but this is actually not so important. But this space is what we want to look at. Okay, and then we want to do the following. We want to look at the accessible regions on this space, the shape orientation space, for given values of the energy and total angular momentum. Yeah? So this R here is the magnitude, the norm of the total angular momentum. So we fix this, and we fix E, and then we ask ourselves, where can we go on this space? What are the admissible points on this space? Okay, so let's show that in terms of a picture. So when we have 3 bodies, then the internal space is actually R3 plus. Yeah, so you can, as coordinates, choose, for example, the interparticle distances. Yeah? You need to satisfy then the triangle inequality, and this way you get, well, this object here. And then in this object we choose this two-dimensional object on which the moment of inertia is actually the polar moment of inertia is equal to 1. Yeah? It's just some choice. So that will be our shape space. And and then we still have the sphere on which the angular momentum lives. Yeah? Okay, so what we want to do is on this space here, yeah, topologically this is a disk. On this disk we want to mark where for a given value of energy and angular momentum you can be on the angular momentum sphere. And on the angular momentum sphere there are three possibilities. Either the accessible region is in caps, in rings, or the full sphere. So we will have three colors, blue, red, and green, corresponding to whether you have caps, rings, or the full sphere on the angular momentum sphere. Okay? Okay, so what is also important to note is that the whole thing only depends on, or this projection, at least topologically, it only depends on this combination of energy and angular momentum. So you can look at the energy times the total angular momentum squared as a bifurcation parameter. And for convenience, you put a minus in front. Yeah? So it all depends on this, what we call nu. It's minus the energy times the angular momentum squared. That follows from the dilation symmetry that you have. So this quantity is actually dilation invariant. Okay, so some pictures. So we first look at the gravitational three-body problem. Yeah. So all these different pictures here correspond to the shape space for a different value of this parameter nu, and we mark what is accessible on the angular momentum sphere. When it is gray, it means that nothing is, there are no points on the angular momentum sphere. It means actually that you cannot, such configurations don't exist for that particular value of nu. That is the gray meaning. Blue, as I said, so that means you have caps. Red means that you have rings, and there are no greens yet on this slide. So what is happening here? We will start with a large value of nu, and that means with a very negative energy if you are fixing the angular momentum, for example. Yeah? And then you have three regions that are accessible. Yeah? So that is familiar a little bit from this picture that I showed at the beginning of the Hill region for the circular restricted three-body problem. If you have low energy, then there's a region near one of the heavy bodies, the other has a heavy body, or outside that is accessible, right? And that are these three regions also that show up here. And then what happens is, if you are decreasing the nu, that means you are increasing the energy, then this region here, the gray region, starts to develop a tangency here, and then it detaches. You can hardly see that here in the picture. Don't try. You cannot see it from there, from your seat, I guess. So what happens from here to there is that this region detaches there, and then this and this is joined. And then there's another critical value where you have a tangency here, and then this detaches, and then you have a tangency there, then this detaches, and then you have, something that is simply, well, it's not simply connected, but all three regions are then connected. Yeah? And then what happens then? Then this gray region, the inaccessible region, if you further decrease nu, then this gray region shrinks or vanishes in a point, shrinks to a point, then it's vanishing, has vanished. And if you then further increase the nu, sorry, I always get confused with the sign. If you further increase the energy, that means you decrease nu, then this blue region, the blue region actually shrinks to a point, and out of this point grows a green region, and this green region is getting bigger and bigger, and it then successively touches the boundary. Yeah? Okay, and this is then, nu equal to 0, and for negative nu, positive energy actually everything is accessible, both in the shape space and on the angular momentum sphere. Okay, so if you have some background in celestial mechanics, then you might have seen such pictures before. Yeah, so in particular, these pictures were used for in order to describe the topology or the bifurcation of these integral manifolds by a famous paper by Meyer and McCord and Wang. So they did a full analysis of all the bifurcations that can occur or do occur. Let me quickly tell you what they are. So there are, if we maybe go backwards, or this is to be read backwards. So there are 3 critical values of nu that are related to collinear configurations, collinear central configurations for the gravitational case. There's one due to the Lagrange central configuration, which is a equilateral triangle. Yeah. So we now have 4. In total, there are, if you take into account also nu equal to 0, there are 10. Then we have one that is due to a critical point, or what is people call a diabolic point of the moment of inertia tensor. So it is interesting to note that the moment of inertia tensor, so for each configuration of your 3 bodies, you have a moment of inertia. Yeah? But this moment of inertia tensor, well, that depends smoothly on the coordinates, but the eigenvalues of it do not depend smoothly on the coordinates. Yeah? So it's not smooth. So it can happen that 2 eigenvalues collide, for example, and then you call that a diabolic point. That notion is used. There is an analogous phenomenon when you are looking at adiabatic quantum mechanics. So you have also that occurring. And then you have so-called critical points at infinity. So what are that? Well, so it's actually these integral manifolds. They are not compact, right? So you do not only need to look at the usual critical points, but they can also be critical points at infinity. So physically, what they just correspond to is, when you look at the gravitational case, at 2 bodies co-rotating and another body at rest, and infinite distance between this pair and the 3rd body. Yeah? If you want to describe that mathematically, well, there was a full paper, so that is actually not so easy. There was basically that has been done by Alboui before. We looked at that then, or generalized that for the charged case. So let me show you now pictures, the analogous pictures, for the case where we have the helium atom. So helium atom described as a classical 3-body problem. So we have the helium nucleus and 2 electrons. Yeah. Okay. So again, we do the same game. We mark what is accessible on the angular momentum sphere. So what happens is that if you start with low energy, large values of nu, there is some gray region, not accessible, and 2 disconnected accessible regions. And then this somehow moves up. It detaches via a tangency here. Then you get this. There's this kind of blue tongue. This blue tongue. From this blue tongue that, so to speak, spits out a blob. Yeah, and so you go from here to there. This blob detaches, shrinks to a point. Another region grows out of this point. That reaches the boundary, and then, it fills the whole sphere. And for energies greater than 0, you have this. So let me come to the end. So. In fact, what you have here is, again, you have critical points that you have seen before. Yeah? 2 bodies, well, the single ionized electron, if you like, rotating, and the other electron far away. These are the critical points at infinity. You always have the diabolic point. Actually, this diabolic point does not create, even though it looks like in this projection, does not create any changes in the topology of the integral manifold. So that is one of the results in the Meyer-McCord-Wang paper. That's quite interesting. That is something one wouldn't expect. But and then you have collinear configurations. Yeah, so it's the nucleus of the helium atom, and then the two electrons symmetrically about the center where the nucleus is contained. But then also you have a relative equilibrium, which is not a central configuration, and that is this one. So you have, let's say this is the nucleus of helium, and here are the two electrons, so the masses are actually then the same, and also the charges are the same, and this whole thing is rotating about an axis that is contained, well, about this line here. So it is not planar. Yeah? It is not planar. And that is an orbit that you can find in a paper by Langmuir, an old paper by Langmuir, when they tried to quantize the helium atom before Schrödinger published his famous equation. So when they tried to do action quantization. And in this original paper, he looked at two orbits, and he disregarded this one because he immediately concluded, well, this cannot be stable. Yeah? I don't know how he came to that conclusion, but he said, we don't consider it any further because it must be unstable. Okay, but in fact, so what we did is have a closer look at the stability of such an orbit. So for arbitrary charges, it's always a symmetric configuration, yeah? Otherwise, for the general case, it will exist, but it's not symmetric. Not symmetric meaning that you don't have equal masses and equal charges here, and it also will still probably exist. But the analysis is extremely complicated. It's extremely hairy. So for the symmetric case, it's already very hairy. But what we got is that the eigenvalue polynomial for this relative equilibrium, so we have an 8-dimensional reduced space. The eigenvalue polynomial is a polynomial of degree 8, right? And we have a Hamiltonian system, so it needs to be, you need to be able to write that as a product of two 4-degree polynomials, yeah, because of eigenvalue, complex conjugate, and minus sign also need to be eigenvalues. But what happens is when you do this splitting, this one polynomial always has purely imaginary eigenvalues. So you always have center times something. Okay? But this something is non-trivial. So this something that is then this polynomial where the coefficients are like this. So you have the masses occurring and the beta occurring. Beta is determined by the charge. And that, so this is actually the beta mass plane. There you can have all kinds of things. You can have saddle centers, saddle saddle, center center. So you have all possibilities there. Now Steve probably would like to ask me, where is helium? And I think yesterday I told you that helium for the Langmuir orbit it is saddle saddle center center. But when I looked at my slides this morning, I'm not so sure about that anymore, because the saddle saddle case, that is region 4. So saddle saddle times the center center from the other polynomial, right? The saddle saddle case, that is, I think, case 4 here. Case 4, right? So you have saddle saddle. That is an extremely narrow region here. So you can always not see that that this is that there actually is a region. The lines lie almost on top of one another. So I would be very surprised if I look at it again that helium is contained in there. But it's certainly possible, well, to have a stable Langmuir orbit if you choose the charges in a suitable way. Yeah, and also you can definitely have, for example, well, what we usually are interested in, the case 3, right, where we have saddle center here times the two centers from the other polynomials, and we will have saddle center center center, and that would give us interesting phase space structures. Okay, let me stop here.
Thank you, Holger. So we are running out of over time, but any pressing one fast question?
How well does this apply to binary systems? How well does this apply to binary star systems? Usually a heavy, medium star, and then a light planet.
Well, that is, well, in the gravitational setting, it's always the same, right?
Okay.
You always find Lagrange, and Lagrange is independent of the mass. It's always equilateral triangle. It's always equilateral triangle.
Okay, thank you so much. Let's thank Holger again. And we are moving to our next and final speaker for the day. I think that it should be, your presentation should be there.
You probably need to. I think he will switch.
So, technician is coming. So, okay, our final speaker for today is Donato Scarcella, and we have a small technical delay.
Okay. Just. It's right? No, it's fine. It's fine. Well, more or less. So, thank you very much for the invitation and for the organization of this very beautiful conference. So, I would like to begin my presentation by proposing you the dynamical model that motivated my work. For this reason, we consider the planar three-body problem, for example, a solar system composed by the Sun with a very large mass and two planets turning around the Sun. In 1963, it is well known that Arnold proved the existence of quasi-periodic solutions for the Hamiltonian of the planar three-body problem. Now, we want to perturb the planar three-body problem by a given comet coming from going back to infinity asymptotically along an hyperbolic Keplerian orbit. The motion of the comet is a given smooth function, and only the planetary system is affected by the comet. So the planets are affected by the motion of the comet, but the comet is not affected by the planets. The Hamiltonian that describes this system is a time-dependent Hamiltonian. It's the sum between the Hamiltonian of the planar three-body problem plus a time-dependent perturbation, which describes the interaction between the planets and the comet. On a suitable norm, one can see that the gradient of this time-dependent perturbation decays polynomially fast in time. So we are considering a time-dependent Hamiltonian system converging as time tends to infinity to an autonomous Hamiltonian system having an invariant torus supporting quasi-periodic solutions. What we expect to prove is the existence of orbit converging in time to the quasi-periodic solution associated to the autonomous system. So this is the model. To this end, we need to introduce the definition of asymptotic and torus. So we consider a time-dependent Hamiltonian on the phase space Tn times Rn. In this talk, we are interested in real analytic and C-sigma Hamiltonians. An autonomous Hamiltonian H0 and an embedding phi 0. We assume that the Hamiltonian system associated to the Hamiltonian H converge in time to the Hamiltonian system associated to the Hamiltonian H0, and H0 has an invariant torus phi 0 supporting quasi-periodic solutions of frequency vector omega. So we are in the same setting of the previous example. The following definition is due to Marta Canadell and Rafael Della Liave. So let X tilde the following autonomous system. A family of reanalytic or C-sigma embedding phi t is an asymptotic M torus is if the following conditions are satisfied. So roughly speaking, an asymptotic n torus is a family of embedding converging in time to the invariant torus associated to the unperturbed system, to the autonomous system, if we consider the projection, the phase space Tn times Rn. And the dynamic on this family of embedding converge in time to the quasi-periodic solution associated to the autonomous system on the invariant torus phi 0. Well, in the following slide, I'm full of remarks and consideration and observation concerning this kind of definition, also a picture. Okay, in order to clarify this definition. So, for this reason, let C H the flow at time t with initial time t0 of H, and we assume that this flow is defined for all times. The first remark is that 2 is equivalent of this. Well, we can rewrite 2 in these terms, where 2 is the invariant equation that an asymptotic n torus has to satisfy. So we can rewrite 2 in terms of the flow of H. This is quite standard, but an interesting consequence is that 2 is trivial. It is always possible to find a family of embeddings satisfying 2. Indeed, if we consider psi hat an embedding, we can use the left-hand side of 1 in order to define this family of embedding. This family of embedding satisfies the condition 2, but we cannot deduce any asymptotic information. Another interesting property is that, I will use this property in the proof of my theorems, if we have the existence of an asymptotic n torus defined for all times, or for all t large, then we can extend the set of definition for all times. The k is always 1. Indeed, the family of embedding psi t defined at the end of this slide is an asymptotic n torus defined for all time because it satisfies the 2 conditions of the previous definition. Obviously, we cannot deduce any asymptotic information concerning negative time. Okay? We have a convergence only at infinity. So, well, in order to summarize what I said so far, an asymptotic n torus is a family of embedded tori converging in time to the invariant torus phi 0 associated to the autonomous system. We are considering the projection of the phase space Tn times Rn. And the dynamic on this family of embedding converge in time to the quasi-periodic solutions associated to the Hamiltonian H0, the autonomous Hamiltonian, on the invariant torus phi 0. Well, if there are no questions, I would like to give you some result concerning this kind of system. The first is due to Fortunati-Wiggins in 2014. They consider a time-dependent Hamiltonian, reanalytic, H. H is the sum between an integrable Hamiltonian H0 plus a time-dependent perturbation decaying exponentially fast in time. Okay? Obviously, H0 has this form, and well, the trivial embedding phi 0 is an invariant torus for H0 supporting quasi-periodic solutions of frequency vector omega. Obviously, H0 has many invariant tori, because it's integrable, but we are focusing on the invariant torus phi 0. They assume the unperturbed Hamiltonian to be non-degenerate. Gamma is a matrix. The frequency vector omega to be Diophantine, epsilon small, lambda just positive, and then they prove the existence of an asymptotic n torus. Well, about 1 year later, Canadella and Della Llave generalized this previous result. They prove, I'm using the color red in order to emphasize the differences with respect to the previous theorem. In this case, they prove this theorem for C sigma Hamiltonians, but it is always true for reanalytic. Well, in this case, H0 is not integrable, but it has an invariant torus phi 0 supporting quasi-periodic solutions of frequency vector omega, and the perturbation decay exponentially fast in time. Contrary to the previous theorem, they do not assume any non-degeneracy conditions on the unperturbed system, any arithmetic condition on the frequency vector omega, and then they prove the existence of an asymptotic M torus. Well, actually, the theorem that they prove is more general than the one I stated in this slide, because they work on Hamiltonian system defined as smooth manifold, and they need to assume a certain control to the normal dynamic on the invariant torus phi 0, controlled by the rate of decay lambda of the perturbation. This is for, yes, to control possibly hyperbolic motion, I think. Anyway, this condition is always satisfied in the case of Hamiltonian system. I'm interested in Hamiltonian system, so I stated the theorem in this way. So, starting by this result with a view to the example in celestial mechanics, the example of the comet, we asked if it was possible to relax the hypothesis of exponential decay in time in the particular case of time-dependent Hamiltonian system. So, during my PhD, I proved in Paris, I proved this theorem. I'm using the color red in order to emphasize the difference with respect to the theorem of Canadel de la Liave. I proved this theorem for C sigma and real analytic Hamiltonian. H, it's always the sum between an autonomous Hamiltonian having an invariant torus supporting quasi-periodic solution frequency vector omega, but plus a time-dependent perturbation. But contrary to the previous theorem, we do not assume any smallness assumption of the perturbation. This theorem is not perturbative. I don't need epsilon to be small. And the perturbation decay polynomially fast in time as 1 over t to the power of L, with L strictly greater than 2. And well, we prove the existence of asymptotic M torus. So, in the last, I think, 5 minutes, yes, I would like to give you an idea of the proof of this theorem. So, we are looking for a parameter capital T sufficiently large and two functions u and v defined for all t greater than capital T in such a way that this family of embedding satisfy the condition 3 and 4, and then it is an asymptotic M torus for associated to our system. I would like to remind you that 3 is the invariant equation that an asymptotic M torus has to satisfy, and 4 implies that this family of embedding converging time to the invariant torus in p equal to 0 associated to the unperturbed system. So there are the two conditions of the definition, okay? Now it is quite clear why we need L strictly greater than 2. And in this slide there is a little spoiler in the sense that we fix the parameter T large enough in order to ensure that the perturbative terms which decay in time become suitably small in order to use perturbation techniques to prove the existence of an asymptotic M torus defined for all time large. Then, using the property of the asymptotic M tori and the flow, we can extend the set of definition for all time. This is the trick in order to avoid the smallest assumption on the perturbation. Well, I will provide you more detail in the following slides, but the proof is new and it's divided into 2 steps. First, over suitable Banach space depending on T. In this first part, T is free. Okay, we will fix it in the second part. We introduce the following functional, capital F. It depends on small f, the perturbations, and U and V, the components of the asymptotic M torus we are looking for. It is defined in such a way that capital F evaluated at small f U and V is equal to 0 if and only if this invariant equation is satisfied. It is the invariant equation that an asymptotic M torus has to satisfy. Obviously, UMV belongs to some Banach space of time-dependent function decaying polynomially fast in time. But I don't want to provide too many details. Well, we have 5. So in this part, we are rewriting our dynamical problem in the following form. For f sufficiently close to 0 on suitable norms, obviously, we are looking for suitable UMV in such a way that f evaluated at small f UMV is equal to 0. So in the first part of this proof, we want to verify that f satisfies the hypothesis of the implicit function theorem. The most interesting step on this first part is the solution of the following equation. Okay, in the unknown key. I'm considering the sigma case. The analytic case is quite similar. So G is a function of class C sigma. This norm depends on T. And is decay as 1 over T to the power of L with L strictly greater than 1. In my theorem, I need 2 because I need to solve this equation twice. We can solve this equation by integration thanks to a suitable change of coordinate which rectifies the dynamic of the torus. On a suitable space of function decaying in time, the solution exists, is unique, and it's given by 6. It is given by integration, so we have a loss of regularity in terms of decay on time. We don't have this problem in the case of exponential decay in time. The solution decay as 1 over T to the power of L minus 1. This loss of regularity, because integrating we lose. If we integrate, we lose a power. This loss of regularity is solved in the nonlinear part because the solutions of the homological equation are always multiplied by some other term satisfies good decay property. So thanks to a series of multiplication, we are able to regain what we lose in terms of decay in time. Well, I cannot provide more detail because I don't have a lot of time, but in the second part of the proof, we fix small f as in the statement of the theorem, and we introduce the following quasi-Newton operator, which appear naturally in the proof of the implicit function theorem. So in this second part, we rewrite our dynamical problem in terms of finding a fixed point of the following operator. So here we fix T large enough in order to ensure that the perturbative term becomes suitably small in order to prove that this operator is a contraction. Okay, so this is the idea. Just to finish, some reference, or is the last slide? Just some, but just one word. I need 1 minute. So the content of this talk is the first paper published in Nonlinearity. The problem of the comet is the content of the second one. In this case, the perturbation in time is too weak. It is not sufficient to apply the theorem that I proposed you today. So this serious difficulty needs the introduction of the generalization of the definition of asymptotic M-Tori and the proof of another abstract theorem where the proof relies on the Nash-Moser theorem. So it's considerably more complicated. Well, I don't have a lot of time, so just a few words on these two. In this one, I proved the existence of motion converging to some quasi-periodic solution in the future, some quasi-periodic solution in the past for time-dependent perturbation decaying polynomially fast in time of integrable and near-integrable Hamiltonian. And in the last one, I'm just considering time-dependent perturbation of an Hamiltonian system having an invariant torus having an arbitrary dynamic. So not quasi-periodic. In this case, we need exponentially decaying time for the perturbation in order to control some hyperbolic dynamic at infinity. So thank you very much, and well, happy birthday.
Is there any pressing question? If not, then we can continue our discussion with the coffee break and some practical.
Yeah, okay, so we have now the coffee break, and at 5:15 whoever wants, we will do the group photo. And then there is a person of the academia that will guide us for a 30 minutes tour. So I think that the poster session is going to be squeezed a bit just for the coffee break and maybe after the visit. But after 6, all of you who have registered for the social program, we will go to the picking point of the bus, okay? So we leave at 6:10, more or less. Before 6, between 6 and 10:06, okay?
And let's thank all the speakers of today's session.